Hello and welcome, I'm your Code Monkey. Welcome to the free intermediate section for my complete C# mastery course. By going through this course, you will learn how to be able to make games, websites, apps, robotics, and literally anything. C# is an extremely versatile language. The course starts from the absolute basics, like how code executes line by line and what is a variable, then covering intermediate topics like what are interfaces, generics, and events, and how you can use them to build some really awesome things. You'll also learn the theory behind how to choose good naming rules, clean code guidelines, and learn about design patterns. And finally, the advanced section, which I'm currently working on and covers quite a lot of advanced topics. Right now, there's a handful of lectures already out, and I'm constantly uploading more. Now, this free YouTube over here, this one contains all the video lectures for the intermediate section. Like I said in the previous video, my goal is to publish the video lectures over here for free on YouTube if the premium version sells a certain number of copies. And I'm very happy to report that it has indeed passed that threshold, which is why this video is over here free on YouTube. I've already posted a video with all of the free video lectures for the beginner section, and in about 1 to 2 months, I will publish the free video with the advanced section. So if you're watching this in the future, check the link in the description to see links for both of those. The premium version of the course has all of the video lectures for all the sections, and also has a bunch of really nice bonuses. So speaking of that, here are the bonuses for the premium version. I came up with some that I think are really awesome, and definitely worth it if you can't afford them, while at the same time not putting any knowledge behind the paywall, so even people who can't afford it, they can still learn from the free video lectures. They really just need to do a little bit of extra work themselves. The premium version is really just selling convenience, making it really easy for you to truly gain the knowledge. The premium version comes with a companion project. This is a Unity project that contains a bunch of extra content. Basically, the video lectures, while being pretty massive themselves, they're still really only half the course. The other half of it is inside of this project. It has a bunch of custom edited windows to guide you through each lecture. And each lecture has a section on frequently asked questions. These are common questions that have some really detailed answers that provide even more details on what is covered in the lecture. Then there are some quizzes. These are multiple choice questions. Again, all with very detailed answers. It's really not just correct or incorrect. If you pay close attention to each lecture, you should be able to get most of these right. But whether you do or don't, by reading the extra explanation that will help you truly learn that topic. Then the interactive exercises, I'm really happy with this feature. I think this will really help you learn. Learning by doing is always much better, and these exercises encourage you to put what you learned into practice instead of just blindly watching the video lectures. I designed a ton of handcraft exercises for all the lectures to help you put into practice and truly learn the contents of each lecture. There are all kinds of exercises. Some are about spotting and fixing errors, others are about asking you to define some function or class or implement some kind of logic. There are some where you just write code, and some where you write code and then play the code in Unity in order to complete the exercise. Then each exercise also contains a hint just in case you get stuck, or a solution in case you get really stuck, as well as a video walkthrough of me going through that exercise and completing it while explaining everything in detail. So if you're the kind of person who gets stuck in tutorial hell, then I truly believe that this will really help you escape it. In order to learn, you need to actually do things, and these exercises encourage you to do that. They encourage you to do it as opposed to just blindly watching the video lectures. Then the companion project also has a companion window. Basically, this window is also listening to a bunch of errors, and if it finds one, it will help guide you in the right direction. I manually wrote a ton of text for when it detects lots of errors, all of them based on common errors that I see people ask about in comments in my own videos. So this should help prevent you from getting stuck in your learning journey and allow you to get help instantly. Then the course also has an AI to help you answer questions. This one was trained on the contents of the course and my own knowledge, so it should be very accurate and helpful. But more than that, it's simply the fact that it is extremely fast. You post a question in the course comments, and within a few minutes, the AI will respond with probably a very good answer. Although, of course, I myself will also still be answering all the questions manually. The goal with this AI is really speed, so you get a response almost instantly, and then within the next few hours, I will manually answer myself. Then a simple bonus is how the premium version has the course split into lectures, as opposed to here on YouTube where it will be one giant video. It has to be that way due to how the YouTube algorithm works. This is a small thing, but it can be helpful, especially if you take your time to slowly go through the course just like you should do. Remember that the only goal is really that you are actually learning yourself. It does not matter how quickly you go through it. So separate lectures help with that so that you can pause and actually try out your knowledge before going further, and you don't have to memorize specific timestamps. And over here on YouTube, the videos have the normal YouTube ads as usual, whereas the premium version has no ads, so there's nothing to interrupt you while you're learning. Another two great bonuses is the private Discord and the live study group. You get access to a private Discord with a really nice community of people all on their own learning journey. I'm there myself as much as I can to answer questions or really just chat. And every week I also do a private live QA. You can join me on the live stream and ask anything you want, and I'll do my best to help. So these are the nice bonuses that I came up with that I think are really nice and really awesome while not taking away anything or putting any knowledge behind the paywall. If you can't afford it, then I highly recommend the premium version. These bonuses will help you truly learn and learn much faster than the 10 years that it took me. But if you can't afford them, that's okay. Like I said, there's no hidden knowledge hidden behind a paywall. You really just need to put more effort in yourself in order to actually apply the knowledge that you gain. So whether you get the premium version or watch the free lectures, I really hope you'll learn a lot. Also, just in case you're new to my channel, so a bit about me and my credentials or why you should listen to what I have to teach. For me, I've been programming for over 25 years and specifically using C# for over 10 years. I'm a professional indie game developer with several successful games published on Steam covering a wide range of genres. My games are usually focused on complex systems since I am primarily a programmer. It's what I really love to do and what I love to teach. Also, a couple of years ago, I started over here this YouTube channel making free video tutorials to basically share my knowledge to help you learn how to make your own games. There's already over 800 free videos over here on this channel if you want to continue learning beyond this course. Also, one very important note for both beginners but also for intermediate users, which is simply take your time, take it slow. Remember, this is your learning journey, no one else's. The only thing that matters is that you're learning. It does not matter how long it takes you, so it does not matter if someone learns all of this much faster than you. You are really not in competition with anyone but yourself. Also, you are not expected to go through this course in 1 day, 1 week, or even 1 month. Basically, all of the content inside of this course, this contains knowledge that took me 10 years to learn. So really, just take it slow, take your time, and really just focus on learning. And one final request, if you find this video helpful, if so, go ahead and hit the like button and subscribe to the channel. It's a tiny thing, but it really does help. Alright, so let's get to the first lecture. Hello and welcome, I'm your Code Monkey. Welcome to the intermediate section where we're going to take things up a notch and learn some more intermediate concepts. But before we do, let me just quickly say, if you are still very much a beginner, if the previous section was your very first exposure to any kind of programming, if so, then just be aware that it's perfectly normal that it takes you some time in order to understand the context of this intermediate section. That's perfectly normal. Learning and truly understanding all that we're going to see, all of that takes quite some time. Remember that the only thing that really matters is that you're learning. How long it takes you isn't really relevant, so really just focus on actually understanding, actually learning. For me, it took me literally decades to learn all of this. So if it takes you 6 months to go through this intermediate section, if so, then you're still going to be doing much better than me. So all that to say, take your time and just focus on learning. Now, if you took a break between the beginner section and this one, then I encourage you to go back and at least rewatch the naming lecture and the clean code principles. I put those two lectures in the beginner section just because I want beginners to be aware of it, but as you grow as a programmer, as you become an intermediate, those two concepts, naming rules and clean code principles, those become even more important to fully understand and fully apply. So if it's been a while since you saw the beginner section, go ahead and rewatch those just quickly. And with that, that's the intro out of the way. So let's go into the next lecture where we're going to see a nice overview of everything that we're going to learn in this intermediate section. Hello and welcome, I'm your Code Monkey. In this intermediate section, we're going to go one level up relative to the beginner section and learn some more complex stuff. So let's see an overview of all the lectures. Beginning with something very important that I debated whether I should put in the beginner section. It's going to be Visual Studio Shortcuts. I end up putting it here because for beginners, technically it's more important to learn how to write the code, and it's not as important to be extremely efficient with how fast you use your IDE. But for intermediates, this is a must-have. So we're going to learn about a ton of shortcuts to help you write code and navigate your environment much better. Then comes one of the most important lectures in this whole intermediate section. It's all about refactoring. This is the process of rewriting your code to make sure it is as readable and understandable as possible. As an intermediate, you absolutely need to know that this is a natural part of the code writing process and something you should not skip. Next is a lecture on enums. Pretty simple and very useful. It's how you can define a specific list of values that you can use in many ways. After that, we'll learn about properties, which are kind of like a mix between variables and functions. Then we're going to learn about multidimensional arrays, meaning arrays that can hold multiple dimensions of data. After that, we're going to learn about nested loops, which is especially important in order to cycle through multidimensional arrays. Next, we're going to learn another method for doing some looping logic. We're going to learn about recursion. This is something that, for people with a math background, it might actually be similar to understand than regular loops. Then we're going to learn about an extremely useful data type, the dictionary. This is a key-value pair that has tons of really awesome use cases. After that, we're going to learn about some more collections like queue and stack. Then we're going to learn about the params keyword and what exactly does it do in a function. Next, we'll learn about optional parameters, how to define them and how to call them from a function. Then another crucial lecture for intermediates. This one is on learning the differences between value and reference types. This is extremely important. If you don't know this difference, then you will go crazy at some point in the future, wondering why something isn't changing, and it's usually going to be because you don't know you're working with a copy and not a reference. Related to that is the lecture on structs. These are similar to classes, but importantly, they are a value type. Next, we're going to learn some more intermediate use cases for classes. We're going to learn about inheritance, polymorphism, and a bunch more. Then learn about interfaces. This is one of my favorite features of C#. It allows you to write some really nice modular code. Related to that, we're going to see various ways of testing for types and converting to and from various types. Also related is the lecture on switch pattern matching. This is a really simple way to do a switch, not just on value, but also on type. Then we're going to learn all about delegates, lambdas, and anonymous functions. This is how we can store a function itself inside a field. Next, we're going to learn the differences between lambdas and local functions. After that, we'll learn about events, which is how we can have one class be notified when something happens. Then the next lecture, that one is going to be all about generics. This is another super powerful C# feature that makes your code work with multiple types. Next is a simple lecture on constants and read-only, what they are and what are the differences between those two. After that is a lecture on exceptions and how to handle them with a try-catch. Then a lecture on implementing IEnumerable, so we can add support for something like a for each for some custom types. Next we're going to learn about namespaces, what they are and how to make your own. Then a really important lecture on one of the most important design patterns, the singleton pattern. And after that is a general overview of a bunch more design patterns. And finally, after doing all of that, we're going to check out the intermediate project that uses all of this to make something really interesting. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn about a bunch of really useful Visual Studio shortcuts. Okay, so as we get to the intermediate stage, it is really important to be good at using your tools. And as a programmer, your main tool is going to be your IDE, so you should be very comfortable with shortcuts and moving around in your codebase. But also this is something that you pick up with experience. So this lecture, this one is really not meant to be a step-by-step lecture, but rather I just want to show you a bunch of shortcuts that I use myself, just so you are aware they exist, and over time you will pick them up and they will become more and more natural. Okay, so the most basic, but honestly most useful one is simply moving the cursor. Normally beginners, they use the mouse to move around, so they scroll down and click wherever they want to write. And then sometimes beginners use the arrow keys and they press it like a million times in order to get wherever they want to go. Technically this works, but it's obviously not very efficient. There are many ways to speed this up, and importantly, many ways to navigate your codebase without your fingers ever leaving the keyboard. For example, when moving left to right, technically you can indeed just press the right arrow key and eventually you will get there. But as you can see, going left to right like this takes quite a while. I gotta press like something like 50 times in order to get to the beginning or the end. So one of the best super simple shortcuts is simply to hold down the control key, and now as you move left and right, yep, instead of going letter by letter, it goes word by word. So that way now I can get to the beginning or the end of this line in just about 4 or 5 presses instead of being like literally 50. So it is literally 10 times faster. Then of course you also have the home and end keys. I use these all the time, especially when combined with shift for quickly selecting something. So for example, if I want to move this line above this other line, if so, then usually what I do is press N to go to the end of this line, then hold shift and press up to select, and now press N again in order to select just that one. Then I press Ctrl X to cut, I move up, press Ctrl V, and yep, like that. So if you do it pretty quickly, it goes quite fast, very easy to do all this. And again, I did all of that without ever my fingers leaving the keyboard. If I were to use the mouse, I would have to select like this, Ctrl X, go like this, and like this. So in this case, not much of a speed difference, but just the fact that your fingers never have to leave the keyboard, that alone is a huge bonus. And again, on all these shortcuts, we're going to see how the difference is usually pretty small, like saving like a second, 5 seconds, or fractions of a second. So that does sound like a super tiny amount, but considering how you're probably going to be programming for many years and you're going to write millions of lines of code throughout your entire life, when you look at it like that, those tiny amounts of time, they really add up. So that's the main thing, just moving left and right, holding control to go between each word, or using end and home in order to go back to the beginning and the end, and combining all of that with shift in order to really move around super quickly. So that's the first tip. And then for something that is sadly not default is moving the cursor up and down. So by default, if you do that, it obviously only moves one line at a time. So again, the same thing, in order to move down 20 or 30 lines, it actually takes quite a lot of pressing in order to move. And by default, the alternative is using page up or page down. Although personally, I'm not a big fan of this. I find that these move the cursor way too much. So every time I press page down, it takes me quite a while to realize where the cursor is and how much actually moved. So I don't like how this moves way too much. So in my code, I added something so that I can move the cursor up and down vertically by just 5 lines. That way I can very easily go down and continue scrolling down, and I'm never lost because the screen never changes a massive amount. I'm always moving down, moving up, select this line of code, do something, move down, write something, and so on. Now sadly, this behavior isn't available by default in Visual Studio, at least not that I know of. So for this, I installed this extension called Visual Commander. This one lets you basically apply some hotkeys to literally anything you can do in Visual Studio. And then with that installed, just go up here into extensions, and here is the V command. And on this one, here are some commands that I made. So here is the window, so I've got move up and move down. So I can edit in order to see what this is doing. And yep, it is executing the command line up, so literally just moves the line up. And the other one, this one does the same thing, but line down. So I've got these two commands. commands. Here, if I have the cursor somewhere and I go into that extension and I use the move up command, yep, it does move up by 6 lines. So then as you can see, I just assigned some keyboard shortcuts to those. So control up and control down. Then I just went into tools, options, and over here go down into the keyboard shortcuts and then find VS command. And up here, command 1, command 2, those are the 2 ones that I made. And as you can see, I've assigned them to control up arrow and control down arrow. So with all that, if I press control up or control down, as you can see, the cursor moves quite a lot faster. So I find this to be much better than just pressing 1, just moves 1 line, or pressing page up, which always causes me to lose and get lost. So with just these steps, you can see how I can move in the code really fast without ever touching the mouse. Like, let's say I want to go down, I want to find, for example, the awake, I want to select the awake, I want to cut it and paste it down here, and there you go, just like this, and remove these lines, format, and so on. So as you can see, just using these, control in order to move between the words, using this shortcut in order to move vertically really fast, and combined with home and end, and with shift and all that, put all those together, and yep, you can move through the cursor, you can move in your code base really quickly without ever leaving the keyboard. Then of course, if you're working on some kind of big file, like for example, this is the player class from my Steam game Dinky Gardens. So this is the pre-massive class. For this one, if I want to get to the bottom, and if I go even with this shortcut, this is going to take quite a while. So for that one, if you want to move a massive amount, you can use Control Home or Control N in order to go to the beginning or the end of the file. So this is yet another way to very quickly move around. And another very useful one for moving around is simply put the cursor on top of some kind of symbol. Like for example, let's say this one, this event on player picked up the experience. And then if you press Control Shift and either up or down, this will move the cursor to the next or previous reference of that symbol. So for example, over here, you can see how it's really useful, how in this huge line of code, this script has almost 1,000 lines of code, but I can very easily see exactly where this one is being referenced. I just move up and down, and yep, here's the definition, and here is where I'm using it. So whenever you want to see all the various places in which you are using some kind of symbol, that can be a function, can be an event, can be a variable, can be literally anything, just hold down Control Shift and then up and down, and you can see all the places in which that symbol is being used. Then another extremely useful shortcut that I use all the time is Control and comma. This one pops out this window, and now here you can search for any class. You just type a name and find it. Like for example, I want to open up the Dinky class, so I'm going to type in Dinky. And now just one thing is this shows actually every symbol. So in this case, in this game, since it's all about dinkies, I've got tons of references to dinkies. So you can see all of these in lowercase. I usually write my variables in lowercase, so I know that's not the one. I know the one that I want in order to open the file is the actual file itself. So I can type in dinky.cs, and yep, that does show the file. Press enter, and yep, here I am in the dinky file. And again, press Control Home to get to the beginning. Yep, here's the dinky definition, and I can see all this code just like this. So if I want to move to like the tutorial manager, so I just write tutorial manager, just write a little bit, and yep, I can already see this one. So this is the class. We can also see the icon over there. So that one means a field, that one means a class, this one means an event, and so on. So I can see this one, press enter, and yep, here I am in this one, and again, move up, move down, and everything works. Again, note how throughout all of this, my fingers never leave the keyboard, I never touch the mouse. So personally, whenever I'm making my games and I want to open another class, I never go into Unity and manually double click on that file. I always do it over here, press Control, comma, search for anything, press enter, and it opens. Or alternatively, for example, that one that I mentioned when you got tons of references, something like over here, tons of references to a dinky, so I can just go into this one, and then I can put the cursor on top of the type itself, and I press on F12, and yep, this one takes me to the class definition. F12 is a shortcut, but if you want to use the mouse, you can also just right click on it, and over here we can see, yep, F12 is indeed a shortcut to go to definition. Now, since we're here with the mouse, one really useful one is over here, the find all references. When you click on this is going to show all of the references to that type. So this can work with whatever is under the cursor. So in this case, I select the Dinky class. So this is going to show me all of the places in my entire code base where the Dinky class is being used. Or alternatively, you can put it just on a field. And yep, now this one is going to show all the places, and you can click in order to automatically go to that line. And of course, it also works with functions. So for example, over here, this function, I'm pressing Control Shift up and down in order to see all the references within this file, but this function is not called from within this file. So in order to find where on earth am I calling this, again, right click, go to references, and yep, I can see, okay, so it's being called from this script right here. Inside the Dinky Manager, it's calling this function. Another really useful use case for that particular one is when working with interface. So let's say I want to see all the classes that implement this interface. Again, right click, find all references, and yep, I can see all of these. Look at these. These are all implementing the iInteractable interface. Then something that I use all the time is Control RR. That is the shortcut for renaming the current symbol. So I just place the cursor, for example, over here on top of the is moving field, press Control RR, and now let's say I want this to be a little bit more descriptive. So is player moving. So I changed that, and note how, again, the other shortcut, Control Shift and up and down, note how this one did rename every single reference of this symbol. So all of those, I don't need to change them, just modify them once, use the rename feature, and automatically renames all of them. And if I find out that the previous one works better, again, just edit, go ahead, remove this, press enter, and yep, there you go, all of those have now been renamed. Remember that refactoring isn't extremely important, and importantly, it's a perfectly normal part of the process. In fact, the next lecture is entirely dedicated to the topic of refactoring. If there is something that you wrote some name, but then later on you think it should have a better name, just take some time in order to rename it. Simply place the cursor over it, press Ctrl RR, write the new name, and it will automatically rename every instance of that symbol. This works on everything from simple variables to even entire classes, and it even renames every single reference in your entire codebase. So for example, here I am on the Dinky class, which is used throughout the entirety of this codebase. I can press Ctrl RR, and I can modify this whole thing and say something, and yep, like it says here, rename will update 297 references in 58 files. So this rename feature is really awesome, really useful. It automatically handles modifying everything, and everything is handled automatically for you. Then when you have multiple windows open, for moving between them, you can use Control Tab. If you just use one, it goes back and forth between the last open tab. So this is something that I use all the time whenever I'm working between two files and I want to quickly move between them. But instead of doing just that and letting go, you can hold down Control and Tab, and as long as you hold down Control, you can see this window, and over here you can move up or down in order to move between all the various windows that you have open. So for example, let's say I want to go into the Dinky Offworld. Yep, there you go. Now I'm looking at this class, and if I quickly Control Tab, I go back into the previous class. And this tab over here, this one only works for the windows that are open. So again, the same thing. If you want to open up a new window, just press Control comma, open the window. Let's say, for example, I want to find the carry vehicle. So I just type in the carry vehicle. Yep, it's right here. Control enter. And this one opens up the carry vehicle class. Now Control tab. And if I want, I go back to the Dinky and move between them like that. Then here's a really simple one. You can raise an entire line by just having the cursor anywhere on that line and pressing Control X. That one cuts the entire line. That one acts as a cut, meaning if you press Control V, you get the line back. Alternatively, for duplicating, you can press Control D. Although honestly, I rarely ever use this one because I can never remember whether it's going to duplicate on the line above or below it. So usually if I want to duplicate something, I just do the shortcuts that I mentioned a while ago. So and, above, and, cut, move, cut, and so on. Now speaking of copy paste, if you press Control, Shift, and V, if you do that, you get a list of your clipboard history. So for example, a while ago I showed cutting the await class, and yep, it is still saved in here. So if I press on enter, yep, it pastes that one exactly like that. So remember that your clipboard has history. It is not just the last thing that you copied. You can access the entire history. Another useful tiny time saver is actually when using the mouse. When using that, if you want to select some kind of word, some kind of symbol, obviously you can do the basic thing, which is just click and hold and drag throughout to select it. So obviously that works, but it's a little bit fiddly. If you move up or down, it can be quite tricky. So the similar shortcut for that, whenever you want to select some kind of word, you can just double click and it selects it, or alternatively hold down Control and click in order to select the entire thing. This can be quite useful, for example, when you have some copy paste code and you want to change some kind of name, but for some reason the rename function doesn't work. Like for example, let's say I want to duplicate this code over here. So right now I cannot use the rename because this one is going to conflict with that one. So instead, let's say the active Dinky list. So I select this one, Control click, and there you go, like that. And if I want, like that. So Control click in order to do Control V and so on. This one can be quite useful sometimes. Then something that I only very rarely use is Shift and Alt. Hold those and then move up or down. And this one basically lets you select multiple lines of code and edit them at the same time. Like I said, I rarely use this, but sometimes can be useful, for example, for quickly appending or removing some kind of prefix. Like for example, on this enum, I've got these values. I want to write all of them and say tier 1, tier 2, and so on. So I can select all lines and write tier and writes on all of them. Or alternatively, if this one did have it and I want to remove them, just select them all and I can remove them. So basically you can write code on multiple lines at the same time. And if you want to quit this, just press escape and yep, back into a single cursor. Another super useful one is when working with events, like for example, the on any Dinky started starving. So I can just write the event name, then plus equals, and then here Visual Studio automatically has a shortcut, so you can press tab to insert. Then if you want, you can rename it, but usually I keep the exact same name that it suggests. So just press enter, and yep, there you go. I've got a new event. Now I can come here and again use the shortcut Control X to get rid of that. Go above, go to the end, press enter, go to new line, then write some new code. So really useful, and if afterwards you decide that you want a better name for this event, again remember just a quick Control RR in order to rename it. Then if you want to find something, of course you have Control F. For example, finding when I'm invoking some kind of event, so just write invoke, and if it finds it, obviously normal. Then the shortcut for going to the next element, that one is pressing on F3, and it goes to the next one, so it finds that one, that one, that one, and so on. In order to go to the previous one, you use Shift F3 and it goes backwards. Also, by the way, this works whether the Control F window is open over there, but if I press on ESC in order to close down that window, and with this, if I press on F3, yep, it still remembers the last thing that I searched. Then for quickly commenting or uncommenting something, you can do Control KC, and yep, it automatically comments that entire line. And if you have multiple lines selected, Control KC, and yep, automatically comments. And the opposite to uncomment is Control KU, and yep, automatically uncomments them. Although personally, I never really use this one myself. Again, it goes back to how I'm so proficient at just moving the cursor. So if I just want to comment all of these, I just do the comment star, go down there, comment star, there you go, just like this. Another useful shortcut is extract method. So you can select a whole bunch of code, then press Ctrl R and M, and this one creates a new method with that code. So let's say setup, and if there you go, it pretty much took that code and placed it in its own method. So this can sometimes be useful. Although again, this is another one that I don't really use myself because again, I'm pretty fast at just moving the cursor. So if I want to do this kind of thing, I really just go into the code that I want. I just go, I move the cursor, move up, move down, then do private void my setup, do some kind of function, then write it just like this, and everything works. If you want to go to a certain line, you can press Ctrl and G. This one lets you input some kind of line number. So let's see, what is that line 500? So just type in 500, and yep, there you go. Here we are on line 500. Now for this one, normally I don't really use it when writing code, but I do use this one quite a lot when writing the text script for my courses. Since normally I write my course in a simple text file, sometimes it has tens of thousands of lines, so for that usually I like to move around by using the line number. Although in the code I never really have such massive files, so I don't normally tend to use it, but it's still a nice thing to know. Then of course the one that you already know, if you make some kind of mistake, Ctrl Z in order to undo, and one you might not know is Ctrl Shift Z in order to redo. Then for moving between Visual Studio and Unity, just a simple Alt Tab, so just once and moves, or if you have multiple files, just keep pressing Tab. And perhaps the simplest and most useful one is simply autocomplete. I really advise you to get comfortable with how autocomplete works. Learn how to just type a few lectures, and then either press enter or dot or semicolon in order to quickly autocomplete. Honestly, I don't remember the last time that I wrote something like, for example, try get component. I just try a little bit and write like that. For example, dinky, just like this, then out, dinky, just like this, super simple. So just get used with how little you have to write in order to press enter in order to automatically write everything else. This works with fields, but obviously it also works with things like functions, it works with classes, it works with literally anything. Okay, so that was a lot of shortcuts. Personally, I use a lot of these all the time, but again, I've been writing code for over 25 years. If you're not used to using shortcuts, then I really don't expect you to suddenly use all of these right away all at once. Like I said, this one is really not meant to be a step-by-step lecture. For the most part right now, I just want you to memorize the first ones that I mentioned about how to move through the cursor quickly. Just memorize those and simply remember that the other ones exist. Then periodically come back to this lecture every once in a while and watch it again. If you do that several times over the next few months, then soon enough, all of these shortcuts that I mentioned, all of these will be natural to you just like they are to me. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn all about refactoring. Okay, so before we learn some more programming syntax, let's cover some very important theory. One of the types of comments that I get most often is basically beginners asking me, how do I memorize all the code and write everything perfectly the first time? And the simple answer is I don't. What you see in a video like this course, what you see is really after I've done tons of research and written, and most importantly, rewritten a ton of code. This is one of the crucial things that separates beginners from intermediates. Beginners think that when the code is written, that's it, it's written forever and will never change, so you have to get it right on the first time. Whereas intermediate programmers, they know that code is a semi-living thing that is constantly changing as your game or your program changes and progresses. Refactoring, which is the term for rewriting code or simply reorganizing it, that one is a perfectly natural part of the process. A very simple process is simply when you first try to build some kind of system, like for example making a health system, at first your primary goal should be simply to get it working. You should obviously try to write some good clean code, but it's nearly impossible to get it perfectly on the first try. So the first goal is just get it working. And now here's the really important step that separates beginners from intermediates. After you get the system working, then look at it, analyze the code, and see if it could be written in a better way. Perhaps there's some variables that could have a better name. Perhaps there are some functions that are clearly doing too many things and should be split into multiple smaller functions. Perhaps you have a whole bunch of data separated that should make more sense being placed in its own custom class. So the first step is indeed just get it working, but then don't forget the second step. That one is how to get it working properly. Remember that your code is a living thing. You won't continue living and working with that code, especially as you start to make bigger and more complex projects. So since you're going to use and reuse that code in the future, make sure you write it properly. It is perfectly okay to write semi-dirty code on the first time. What is not okay is to leave it dirty. So when it is working, take some time to do some refactoring if needed. So if you are a beginner about to transition into the intermediate stage, I want you to truly learn and fully internalize this. It is perfectly fine. In fact, it's essential to rewrite code. You are not expected to write everything perfect on the first try, but you are expected to constantly be thinking about how the code could be improved, and if you do find some possible improvement, take some time and refactor that code. Always keep that in mind, especially as we go through this intermediate section, which naturally will increase in complexity compared to the beginner section. So keep that in mind, and let's go to the next lecture and learn about enums. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn one super useful feature of C#, which are enums. These allow you to define an enumeration with a set of named constants. It's really useful in so many scenarios. Okay, so enums are really great. Like, for example, look at this code, this function over here, get next player action. This is supposed to be something like a turn-based strategy game. So the player has this function and uses this in order to calculate what is the next player action, then does a whole bunch of tests to find out what is the next valid action, and doing so it returns an int, which is going to be some kind of code for whatever action the player should be taking. So for example, the player checks if it has no enemy. If so, then it returns 0, so 0 means no enemy. Then checks if there's no path to the enemy. If so, returns 1, so 1 means no path to enemy. Then checks within attack distance, so 2 means moving towards enemy, or 3 means attacking the enemy. Now, the big problem that is immediately apparent in this code is that returning an int value, that one is really not very intuitive. Int is really supposed to be a number, so matching an int to some kind of behavior, that seems quite strange. Just like this, you have to memorize that 0 means no enemy, 1 means no path, and so on. So numbers really are not the best type to use here, and instead this is one of the many scenarios where enums are really excellent. So first we define an enum, and the way we do that is we just type in enum, then the name of the enum, so for example let's say player action, and then open and close the curly braces. And now here we just define a set of names for our various enum states. So for example in this case we want one to represent no enemy, we want one to say no path to enemy, and we separate them with a comma, and one moving toward enemy, and finally attacking enemy. Alright, yep, just like this. So now we have defined an enum, which inside can have 4 of these possible values. By the way, the enum, just like classes, just like types, just like anything, also can have an access modifier. So again, the same rule, if you don't need it to access from anywhere, make it private. If you do need to access it from somewhere, make it public. Okay, so like this, we have defined our enum. Now we can refactor this code in order to make it much more understandable. So for example, instead of returning an int, let's return of type player action. Then over here, instead of returning a number, we just return player action dot, in this case, no enemy. So instead of having this, we just have this. And yep, right away, this makes a lot more sense. So let's apply the same thing to all of these. So this one is the no path to enemy, and this one is going to be the moving toward enemy. And finally, we have the attacking enemy. And yep, just like this. So now we don't need those comments to explain what the number is supposed to mean. Just looking at the actual value itself, just like this, we can understand what exactly this is meant to be doing. So enums really are this simple. We just define the values for our enum and then use it in any way we want. By the way, here we are returning an enum, but an enum is really just a type. So we can do anything we want with it. Like for example, we can make it a return type for a function, or we can just make a variable of type player action, and we can set it to one of the values in our enum. We can use it as a parameter. We can use it on pretty much anything we want. Anything we can also use any other type in. Then another very common use case for enums is doing something like a state machine. So for example, let's define a private enum for the state. And on this state, let's say we have the state looking for enemy. Then we have moving to enemy, and finally attacking enemy. So these are our various possible states. And then we have some kind of function to handle the state. So this is going to handle our state machine. And over here, we just do a switch and do a switch on our state. So we would have some kind of state variable holding the current state for this unit. And then we do a switch on that state and do case something. So case, for example, moving to enemy. Then we have the moving to enemy logic. Afterwards, we do a break. Then we do all the other cases. So looking for the enemy and so on. So yep, this is a really simple state machine, and you can see how by using an actual enum for the state, that makes it much easier to understand as opposed to if we had the state being some kind of int. And over here, instead of these, we would have just 0, 1, and 2, and we would have to memorize what these numbers mean. So just looking at this, it is very clear just how good enums are. With numbers, it becomes really messy, but if we apply some enums, everything looks really understandable. Now, enums also have an interesting property, which is on the back end, these values are actually stored as ints. So to run some testing code, over here I'm writing some code in the Unity project. So let's just do a private void start, which is going to run this function automatically. So now over here, for example, let's define a player action, just a field of player action, and let's set it to something. For example, let's say no enemy, which is the first one that we defined. So we define this, and now let's do a debug.log on this player action. And if we do this, and up here in the console, we can see it pretty much print out a string of the state, so no enemy. However, like I said on the back end, these values are actually stored as ints. So if we cast this down into an int, let's see what this one says. And yep, the int is going to be 0. However, instead of printing out the int for no enemy, let's say the one for no path to enemy. So this is the second state that we defined. And yep, this one now prints 1. So the order is based on how you define them. So the first one is going to be on essentially index 0, then 1, 2, 3, and so on. And you can also do the opposite. So we can, for example, let's cast onto a player action, and let's cast, for example, the number 2. And if casting the number 2 onto our enum does return moving toward enemy. So due to this property, due to how enums really are stored as ints in the backend, because of this, there are some interesting things you can do with it. For example, another common use case for enums is when making some kind of game tutorial with various stages. So you'd have an enum for the tutorial stage, then have like stage 1, which is like player teaching the movement controls, and stage 2, stage 3, and so on. So you'd have this kind of thing, and then you would define some kind of variable to store the current tutorial stage. So let's say we're starting off on stage 1, and then we can just do tutorial stage ++, and let's do a log on this one. So we're defining it as stage 1, then we're doing ++. Let's see what this one says. And if it says stage 2, so it went on to the next enum value. Then we could simply compare against the last value in the tutorial stage in order to know if we've reached the end. Alternatively, you can also handle the conversion back and forth using strings. So for example, a string for the tutorial stage string. And here let's grab the tutorial stage and call the usual toString function. So this is going to convert onto a string. And now if we take this and we try to cast it to tutorial stage, if we do it, then nope, this does not work. This is an error. We cannot automatically convert a string into our enum. So if you want to do this, the correct way to do it is go inside the enum class. This one exists inside system. So you go inside of this one, and then there's a parse or a try parse. So the only difference is this one returns a bool whether the parse succeeded or not, whereas this one assumes it always succeeds. And you can see these also have versions with these angled brackets. These are generics, which I'm going to cover in more detail later on in this intermediate section. So for example, since we know that the code perfectly matches the tutorial stage, let's just do a parse. We're going to parse onto the type of tutorial stage, and we're going to parse this string. Okay, so if we see this, we should be able to see the usual stage 2, because we got stage 1, we increase it, convert it into a string, and then from a string back into our enum. And if there it is, correct. Then yet another thing you can do with enums is simply cycle through all of the possible values. And for that, we can do, for example, a for each inside the tutorial stage. Let's cycle through all the tutorial stages. Then in. And now here you can't do, for example, tutorial stage.count.something. No, that doesn't happen. That doesn't work. So instead, in order to get all the values, you go again inside the enum class. And for this one, you can pass in get values. And this one takes in a type. So here to get a type, we want to type tutorial stage. But just like this, nope, this does not work. In order to get the actual type object, for that, we use the keyword type of and pass in our tutorial stage. So yep, like this it works. So debug.log on this one. And this should print out all of our possible elements inside our enum. So let's just print some and just separate from the other logs. Let's see. And if there it is, stage 1, 2, 3, and 4. All right, so those are enums. Really useful in so many scenarios. They are really easy to use and help you make your code a lot more readable and understandable. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn all about properties in C#. These are kind of a mix between a variable and a function, so you can store some data and run some logic. Okay, so properties, these are actually pretty simple to define. So we define them pretty much like a normal variable. So we've got the access modifier, so let's make it private. Then we have the type, let's say of type string. Then we give it some name. And the usual naming rule is for properties to use Pascal case, meaning uppercase on the first letter. So for example, player name. And then if we just put a semicolon, if we just do this, then this is a normal variable. It's not a property. In order to make it a property, instead of this, we open and close a code block. And now here we add two pieces of logic. One is called get, so let's do get and then a semicolon. And then the other one is called set, so let's set and then a semicolon. And if that's it, this is a super simple property. And in order to use it over here in our static main function, let's just define this one as static. So then down here in our main, we can use it just like as if it were a regular variable. So we can go inside the player name and we can set it to something like Code Monkey. So let's do this and then do a console.writeLine and let's print out the player name. Okay, let's see. And if there it is, and does print out the name, so pretty much the same as a regular variable. However, in reality, this is not a variable. In reality, the C# compiler is doing a little bit of magic in the background. Properties are really not variables. They don't actually store any data directly. So what we have defined here is what is called an auto-implemented property. In the background, the C# compiler is generating a hidden variable that does store data for this property. So we can also just manually do exactly that. So let's do a private static string for the player name. And again, since this one is a variable, we're going to use camel case. And then let's use it over here on the property. So inside this code block for this get and this set, we can actually expand upon it. So for the get, let's add a code block inside it. And over here, let's return our backup field. So let's just return the player name, the underlying one, okay. And then for the set, again, same thing, let's add a code block. And for this one, we want to set the player name, so player name equals, and then we use the keyword value. So this is basically going to be whatever value we assign to the player name. So when we run this line of code, it is going to run this sort of mini function, and it's going to assign the value to whatever we assign here, which in turn is going to assign it onto the underlying value. Okay, so if we test like this, and yep, everything still works the same. It still prints out CodeMonkey. So what we have over here is literally exactly the same as we had previously. The C# compiler simply builds all of this automatically in the background whenever we do a property where we have just a get and just a set, and we do not define any of these code blocks. Now here, the get and the set, these are pretty much functions, which means you can write pretty much any code here. For example, we can do some validation. So over here on the get function, for example, let's test if the underlying player name equals null. So if it hasn't been set, if so, then we can return some kind of default, so unknown. If we do it like this and we erase the setting, so we just have the player name uninitialized, and if there it is, now it does print out unknown. So we basically added some extra logic onto our get function. And when setting, same thing, we can also validate the value. For example, let's say this player cannot be named CodeMonkey. So we can test if the value equals, for example, CodeMonkey. If so, then either we can set the value to some default value, or for example, we can throw a new exception, cannot name player CodeMonkey. By the way, I'm going to cover exceptions in detail in a future lecture. This is pretty much just an error message. So if down here we can try to set the player name equals CodeMonkey, if we try doing this, and if there it is, right away we see an exception, because again, it is running our validation code, and our validation code does not let us rename this. So usually this is the goal of properties, which is how you can do some validation for processing either the get or the set function. And one extremely useful thing you can do with properties is simply make different access modifiers for each of these. Now, right now, we made the player name, we made this one private, which means that both of these are going to be set to private. And if instead we make this public, if so, then now both these are public, meaning any class in our codebase can access either the get or the set. However, you can also add different accessors here. For example, we can leave the get like this in order for anyone to access it, and we can make the set as private. That means that this class can now access and set the value over here on the player name, but other classes can only use the get. So yep, here we do see an error. So I created the completely separate class named player, and inside I'm trying to access the player name and modify it. Nope, I cannot use it because the set accessor is inaccessible. However, if I do a console.writeLine on this one, if I do it, then yep, this is perfectly valid code. So this property can now be accessed. We can access the get from any class anywhere in our codebase, but only this class can access the set. So right now you might be wondering, okay, so is this really all the same as just making a field with some get and set functions? And yeah, pretty much it is. If we were to make a private static void set player name and receive a string for the player name, if we do this and set the player name, and then we have a private static string for the get player name, and over here we return our player name. So if we have this code and then up here, let's say we don't want any of this validation, so we just have the basic auto implement property, so just get and a set. So yep, just like this, the property that we defined up here, it is doing pretty much exactly the same thing as what we have down here. We have a field with set and get functions, and that's pretty much the same thing that we have here. So these two pieces of code, these are pretty much identical. Now, I have to say that personally, I'm not a big fan of properties, simply because I do not like how they look like variables but act like functions. Personally, I find that needlessly confusing. If I want to store some data, I want to use a variable, and if I want to use some logic, I want to use a function. Combining both in a strange way, to me, just seems really odd. It seems needlessly confusing, but that's really just me, that's just personal preference. A lot of people really like using properties. In fact, the official C# documentation is full of properties. So while personally I don't like them and don't normally use them, it's not because they're bad, it's really just personal preference. So if you do like them, feel free to use them in your projects. For me, the only place where I use properties is when I use the singleton pattern. I'm going to cover that in detail later on in the course, but over here, let me just quickly show you how the property helps implement that pattern. Usually in that pattern, you want some field to store the singleton reference, but importantly, you want only the singleton class to be able to set that field while anyone else can get it. So the property accessors are really useful for that. So usually for that, you make a public, make it static for the singleton pattern, make it of the type that you are making the singleton, so for example the program type, then you usually call it instance, and then we have a get and a private set. So yep, this way the access is exactly as intended by that pattern. We have a public property with a public get and a private set, meaning this one can only be set inside of this class, but any other class can get it. Like I said, I cover singletons in detail in a future lecture, but I just want to show that this is pretty much the only scenario where I use properties. For anything else, I normally just make a regular field, and if I need to, I make get or set variables if I need to modify. But again, it's all personal preference, so if you like properties, then go ahead and use them. Okay, so that's properties. They are a really interesting mix between a variable and a function, allowing you to handle stored data and process it in some way when getting and setting. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn about multidimensional arrays. Okay, so in the basic section, we already learned about arrays. This is how we can store multiple pieces of data in just one variable. We've got essentially multiple containers at each different index. So now we can just go one step further and essentially make multiple dimensions of these arrays. For example, we can make it have 2 dimensions, so it has 2 axes. And then each position, instead of having just 1 coordinate, it actually has 2. So for example, on this array, we can go into position 0, 0 and place some kind of number. Or we can go into position 2, 3 and place some kind of number. Go into 4, 1 and draw something, and so on. So each of these positions works exactly the same as the elements in a regular array. They can be set or you can get their value. And this is an example of a 2D array. So you've got a certain axis and another axis. But you can have as many dimensions as you want. You can have a 3D array, 4D array, 5D, 6D, or literally anything you want. However, this is also just one type of multidimensional array. There are multiple types and multiple ways to build them. So this is the syntax for building a regular one-dimensional array. So int, then the square brackets, int array, then create an array with some kind of size. And one way to make a multidimensional array is to make an array with multiple dimensions. So to do that, here when we define an array, we include a comma for the dimensions. So in this case, we have 2 dimensions, so one on the left side, one on the right side. Technically, there's no limit, so you can add as many dimensions as you want. So here, let's do a simple 2D array. So we do that, and then afterwards, we just include the size for both dimensions. And yep, like this, we have a 2-dimensional array. On the first dimension, it has a size of 5, and on the second one, it has a size of 6. This creates the array, and then in order to modify a certain index, we can just access it with the coordinates. So go inside the int array, and now on a flat array, you would just put an index, but this one is multidimensional, has 2 dimensions, so we need to put the index for both dimensions. So for example, 0, 2, and yep, this will access the element inside the array on position 0, 2. You can use this to read the value or assign it to something else. Then when it comes to arrays, you will eventually want to cycle through them. And normally you would do some kind of for, so for int I equals 0, I less than the int array.length, do this plus plus. So normally this is how you would cycle through an array. However, now with a 2-dimensional array, if we do this, then this one, this int array.length, this one is going to return the total length. So in this case, it is going to return essentially 5 times 6. So we can do a console.writeLine to see. So the int array.length, and if there it is, the result is indeed 30, which is 5 times 6. So that's the total size of the array. When we have a multi-dimensional array, in order to get the length of a single dimension, for that we can access the function getLength. This one, as you can see, takes a parameter for the dimension. So let's first cycle through all the elements in the first dimension, and then inside we can do another for loop. By the way, I'm going to cover nested loops in detail in the next lecture. But yep, just like this is going to cycle through every element in the entire array. It will cycle through the first dimension, then the second dimension, in order to go through every single element. We can do a console.writeLine and print out the int array on position I and j. This will print out the value stored in that coordinate. Let's also just print out the I, then comma, then the j, then something, so we can see what we're seeing. Okay, let's see. And if there it is, we can see it all working. So first checks position 0, 0, then 0, 1, 0, 2, and so on, until it gets to 1, 0, so on and so on. And all the values are just 0 because we just initialized all with 0. But as you can see, this is indeed cycling through the entire array, through both dimensions of our multidimensional array. Alternatively, for initializing the array contents, we can do this. Note the difference between this syntax and the syntax with just one dimension. So here we have some curly braces, and then inside we have multiple pieces of curly braces, one for each of the second dimension of the actual array. And up here we can see the array being initialized. So in 0, 0 has 1, 2, 3, then on 1, 0 it has like that. One crucial important thing about these kinds of arrays and initializing it like this, the shape needs to match. So on the first one, if we initialize this with 4 elements, then the second one also needs to have 4 elements. In order to have multidimensional arrays with differently sized elements, for that we can use jagged arrays, which I'm going to cover in a little bit. But before we get to that, like I said, there are multiple ways of doing multidimensional arrays. This is just one way where you have a single array with multiple dimensions, and the other common alternative is simply to have an array of arrays. So instead of int and square brackets and having a common, we have int and then square brackets, open, close, and then open and close again. This is basically creating a new array of arrays. Then we can do the usual cycle through it. So for int I equals 0, less than array.length. Here we can use length because again, this is not a multidimensional array. It is an array of arrays, meaning it's an array, and inside each position, each element itself is going to be an array of multiple elements. So we can do this, I++, and we can go int array on this index, and inside it, we create a new int array of whatever length we want, like for example 6. So basically what we have here is what we had previously when we had a multidimensional array with 5 and then 6 on the other dimension. And then for accessing this one, we access it by int array, then access the first dimension, like say on position 0, and then the second dimension, let's say on position 2. So yep, this is how you set or read some elements from an array of arrays. So this is also a valid way of storing multiple dimensions. Instead of having just one array with multiple dimensions, you have multiple arrays of arrays. And of course, the same thing that I said a while ago about having no limit to how many dimensions you can have, that still applies here. So you can have as many arrays of arrays as you want. So this code looks pretty insane, but yep, this is perfectly valid code. One crucial difference about these two types is basically the defaults that they will use. For example, down here, when we create an int array with multiple dimensions, when we do this, by default, all the elements inside of this array won't be on 0. So yep, like we see, all the elements default to 0. Whereas on this one, since this is an array of arrays, if we just cycle through the main array, if we try to access this one, so let's do a console.writeLine on this one. So let's print out the array on this index. Let's do that and see what this prints out to see basically what each element of this array defaults to. And if there it is, the answer is essentially null. We can compare this equals null. And if there it is true, so all of these elements are set to null. So that is one big difference between array of arrays and multidimensional arrays. These get initialized with every value at 0 on whatever type you're using for the array. Whereas this one, since each element inside of the main array, since each of those is actually an object, it's actually an array of something else. Because of that, by default, the default value for some kind of array is going to be null because arrays are reference types as opposed to value types. Which, by the way, I cover value and reference types, what those are, I cover those in detail in a future video. And then another difference between these two types. One thing that you can have with array of arrays, but you cannot have with a multidimensional array, one of those things is what is called a jagged array, meaning each subarray can have a different size. Down here, when we define this multidimensional array, by default, the shape of this array of multiple dimensions, the shape will pretty much be a rectangular size. So over here, 5 in one dimension and 6 on another one. It will always have some kind of rectangular shape. However, in an array of arrays, that does not have to be the case. For example, when initializing this, we can set the one on index 0 to be a new int array, and let's say this one has a size of 3. Then on the next one, on element index 1, we can say this one has a size of 6. Then on index 2, we can say this one has 10, and so on. So using an array of arrays, technically each array inside the main array, each of those can have whatever size you want. As for what use case this would have, for example, imagine some kind of grid for a theater. When you go to the movies and select a seat, usually different rows have different number of seats. So that's an example where this kind of data structure could be useful. You would have maybe 3 seats on the first row, then 6 on the second one, and so on. So that could work. It does have some use cases. Although personally, I pretty much never use them, since in games, usually things have some kind of rectangular shape. Things like an inventory or a world, usually those have some kind of rectangular shape as opposed to some weird jagged shape. Now, when working with multidimensional arrays, we need to cycle through them just like we saw. So let's learn about nested loops in detail in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn about nested loops. Okay, so let's see what they are. They are really simply just a loop within another loop. So for example, let's do a for loop for int I equals 0, let's say less than 3, I++, so a regular for loop. And then inside it, we can write another for loop. Let's say int j equals 0, j less than 2, j++. And by the way, usually the convention for these iterator variables, usually use the variable I, then you use j, then if you need more, you need k, l, m, n, and so on. That's usually the standard convention. But it's not a requirement, it's really just a convention. So these can be named whatever you want, but in general, I and j are very commonly used. So over here, let's do this. Let's do a loop inside another loop. And now let's print out the I and j to see exactly how this code is running. So let's print out I, then a little comma, and then j. Okay, let's see. And if there it is, so we start off with an I of 0 and a j of 0. And then we have an I of still 0, but then a j of 1, meaning that for each time this loop is running, this one is going to run as many times as this loop is meant to run. So it goes inside this, runs this line. Then when this one ends, goes back into this for loop and runs this line again. Then this one reaches the end, so that is why this one ends and again goes back into this one, which again runs this loop starting from the beginning and runs more and so on. So here it is running 0, 0, 0, 1, 1, 0, 1, 1, 2, 0, and 2, 1. The important thing to remember here is the code execution order, meaning for every time the outer loop runs, the inner loop is going to run multiple times, 2 times in this case. Also remember what we covered in the basic section about variable scope. If you define some kind of variable inside this inner loop, like a int age equals 5, if we do this, and down here you try to access the age, nope, that does not work. If you define something inside the scope of this inner loop, it does not exist outside of it. And here we have one nested loop, but technically we can have as many as we want. Again, the same logic. For every time that this loop runs, any loop inside of it will run as many times as those run. As you can imagine, if you do a ton of loops within other loops, if you do that, it becomes really hard to understand the logic the deeper you go. So usually just having one nested loop, in most cases that is the most you should do. Then we already saw these briefly being used in the last lecture covering multidimensional arrays. That's a very common use case. So here it is, that same code. So we've got the outer loop going through the first dimension, and then we got the second inner loop. That one is going through the second dimension. And by doing this, this is going to cycle through every element inside of this multidimensional array. Then on loops, there are 2 important keywords. One is called break, and this one breaks out of the innermost loop. So for example, if we don't include the break, let's see how many times this prints with the value on j. And if there you go, the value on j goes from 0 to 1, 0, 1, and so on. But if we add a break over here, and if there it is, now the j only goes to 0 and immediately breaks out of that inner loop. Now the important thing to note here about break is how it only applies to the innermost loop. So this one does not break out of the outer loop. As you can see, the outer loop still runs 0, 1, 2, and so on. So break only affects the innermost loop. If you do want to break out of the outermost loop, if so, you can define some kind of bool, break from loop. You set it to something like false. Then inside this one, you do some kind of logic that would eventually set this one to true. And then down here, you would test that. And if so, then call break. And let's see. And yep, now this one does go inside. As soon as it goes inside, sets that break to true and breaks from that one. So breaks from the inner loop, and once this one is true, it also breaks from the outer loop. Now the other important keyword is continue. This one continues or pretty much skips to the next iteration of the loop. So if we write some kind of code after this continue, so let's do a right line and write something like this. Even Visual Studio is telling us, so this line is slightly faded because it will never run, so unreachable code detected. That is because as soon as the code gets to this continue, it is going to ignore everything afterwards inside this loop and go to the next iteration of this loop. So if we run this, and if there it is, it runs through every single element, so the j is always 0, 1, 0, 1, and so on. But note how our second message, this one did not ever show up. If we were to put this inside some kind of if, let's say if I equals 0, then continue. So basically on the first I, when the I is 0, then it should not print this message, but on the other ones it should. And if there it is, so whilst on 0, it is going to continue and ignore this line, but on the others, it is going to run this line. And again, same thing as previously, note how this one only applies to the innermost loop. Even when we're running our continues over here on I of 0, note that the I still runs all of them, so 0, 1, 2. So again, always remember that break and continue, those only affect the innermost loop. Now I should also say that break and continue are not specific to just nested loops. You can use these keywords with any loop, including just a single regular for loop or some kind of for each. For example, if we have some kind of player class, so for example, here's some simple code. So we've got a basic player class, then we create a list of type player, then we create a new special player, we add that special player onto the list, and then 3 random players. Then we do a for each inside of that player list, cycling through every single one of them. And then we check if that one is a special player. If so, let's continue. If not, let's write in the name. So if you do this, we should be able to see the print of only 3 players and not the special player, because that one will be skipped over here on the continue. And if there you go, exactly that, 3 players and no special player. Now also on the topic of nested loops, here we have a for inside another for, but you can list any loop of any type. So for example, over here we can have a for inside another for, and then inside both these fors we've got our for each, so this perfectly works. Or we could replace this with a while or a do while, so literally anything works. So as you can see, nested loops can be really useful, especially when cycling through multidimensional arrays. But if you go too deep, if you nest too much, it can negatively affect code readability. If that's the case, consider whether you really need to make that nested loop, and if so, perhaps consider making a function that in itself has a loop. Then within some kind of outer loop, you just call that function. So just be aware that nested loops can become messy very quickly, so do be careful to use them properly and only when needed. Okay, now that we've learned some more advanced use cases for loops, we are ready to learn something that some people find quite complex, which is recursion, so let's learn that in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn about recursion, which is a different way of doing loops or just running logic multiple times. Okay, so recursion. This sounds like a really fancy word, but in terms of logic, it's really super simple. It really just means a function that calls itself. So for example, over here, let's make a function. So private static void, let's call it test recursion. So we have this function which does some kind of thing. And then inside this function, we call itself, and up here we call the first function. So yep, that's it. This is recursion. It's pretty much just a function which inside calls itself. Now, right away, you might be able to tell a big issue here. You can probably already tell that this is going to be an infinite loop, since this function will call itself for infinity. And actually, if we try to run this code, we actually get a fun piece of trivia. Yep, here we have an infinite loop that eventually ended, and it ended with this error, a Stack Overflow exception. And yep, this is where the famous website got its name. Basically, as you call functions, your CPU stores references to those functions in something called a call stack. That's a stack of all the functions that have been called in the current process. The CPU needs to know that so that it knows that when a function ends, where should it jump back to. But of course, memory has a limit, so if you call a function within a function way too many times, eventually you reach that maximum, which then causes the stack to loop back, which in turn is called a stack overflow. So with this code, we have an infinite loop, not very useful. But like we already saw in the last lecture and in the beginner section, loops can be extremely useful. And recursion is really just one type of loop. So with recursion, we can do literally anything we can do with normal loops. For example, let's write a while loop. Let's increase some kind of number one by one until 5. So here we have a simple while loop, so we define number of 0, and while the number is under 5, we just increment it. So that's it, pretty simple. Now let's do the exact same thing using recursion. So on this, we have a function. And really, since recursion is all about a function calling itself, all we really need to do is pass in our variable as our parameter. So we can just receive an int for the number, and inside do number plus plus. However, just like this, it won't work, since like we saw on the lecture on scope and functions, function parameters are actually local variables. So when we call this function with this, we're working with a copy and not the original data. So to get some kind of result back from our function, let's simply set it as our return type. So let's return of type int. And then here we can do our logic and basically then do return number in order to return the final number. So now when do we want to return the final number? So now let's do the same condition that we had up there. So if number is under 5. So we do if number is under 5. If so, then we're going to call test recursion again, and we're going to return it with number plus 1. And in order to get the data back, let's call a return on this. And if not, if the number is above or equal to 5, if so, let's just return the regular number. So just like this. Let's just give this a proper name, so let's rename this to recursion incrementer. Then up here, let's call the same thing. And we're going to start off by calling it with number 0, and let's do a console.writeLine on this to see the result. So let's see the result on this one, and also a console.writeLine on the other number made with the regular while loop. Okay, so let's see if both these do return 5, and if there it is, they both return 5. So we both have this logic that this one is going to run this logic multiple times, and this one is also going to run the same logic multiple times. So over here, as we call this, the first time number is going to be 0, and if number is under 5, if so, then this one is going to return the result of this function, and this function call will pass in the number, so 0 plus 1, pass in number 1. So once again, that is going to go inside this function, now with the number 1, which again, still under. So it is going to return another call of this function, which again, with the number 1 plus 1 equals 2, and so on. And as soon as it gets to 5, just returns the final number. So basically here we are stacking multiple function calls on top of one another. And when the final one returns, they all basically return and the call stack collapses and we end up with the final result. Then if we wanted, instead of having a hard-code maximum over here, we could have another one as a parameter. So an end for the number max. So we have that and we receive it here and we just pass it along the same way onto the next function call. And then we could also have a parameter for the incrementer, so increment amount. So we have this one, and instead of increasing by 1, we increase by the incrementer amount. So then over here, let's put it 5 and then 1. And over here, let's also pass in the incrementer amount. And yep, same result, 5, 5. And what we have built here is essentially the exact same logic as some kind of for loop. If you remember, the for loop has some kind of initializer iterator variable. Then it has some kind of condition, usually some kind of maximum number, and it increments by a certain amount. So what we have here is literally the exact same thing as a for loop, except it's being handled with recursion. So all the logic you can do with any kind of loop, you can do with recursion. This is really just an interesting way to handle running logic multiple times by simply being very clever about how a function can call itself multiple times. Now, I should also say that personally, I'm not really much of a fan of recursion. In general, I find it needlessly confusing. I much prefer to have a simple for loop where I can very easily see the iterator and the end condition. as opposed to having to look at the parameters for a function and trying to guess when it will stop calling itself. So personally for me, I pretty much never use recursion. I always use just regular loops. I find those much more straightforward. But recursion is a valid option, so I definitely wanted to cover it, especially if you're into advanced mathematics. If so, then you might actually like it, since mathematics has a lot of this kind of stuff. If you like that, then perhaps for you recursion might be much more natural, much more intuitive than working with regular for loops. Just always be careful, the same issue with for loops, which is always be careful not to end up with infinite loops. Hello and welcome, I'm your Code Monkey. In this lecture we're going to learn about one of the most useful collections, the dictionary. Okay, so dictionaries are a super useful data type for storing multiple pieces of data and doing so in a very organized way. Dictionaries are all about key-value pairs, meaning that the dictionary itself is a whole container, and inside that container you store various keys, so like some key for stone, some wood, and some gold. And then for each key has a corresponding value, and then that value can have whatever that you want. Importantly is both the key and the value. Both these can be of whatever type you want. So for example, in some kind of game storing the resource amount, the resource type itself can be the key, and the amount that you're currently holding, that one can be the value. If you were to build something like that using an array or some kind of list, if so, then you would have to memorize it. For example, index 0, that one refers to wood, index 1 refers to stone, index 2 to gold, and so on. So you'd have to memorize what type each index belongs to. Whereas with dictionary, the key itself can be very descriptive about what value it stores. You can use a proper name or a proper object reference. That makes a lot more sense than keeping in mind what index belongs to what. Now to build a dictionary, this is actually super easy. We just type in dictionary, and then we open up the angled brackets. Now this syntax, these are generics, kind of like we use on the list. I'm going to cover generics in detail in a future lecture in this intermediate section. So we open the angled brackets, and then we have two types. The first one is going to be whatever type we want for our key. So for example, let's define an enum for that. So private enum for the resource type. So we have this, and then inside for the values, let's go with stone, then wood, then gold. Okay, those are the values for our resource type, and over here we can use that resource type itself as our key. And then for the value type, let's say we just want to store the amount, so let's use a simple int. So let's name this resource type amount dictionary, and then we can simply construct it. So just new dictionary of this type. Okay, just like this. So this is going to create our dictionary, but so far it's going to be just empty. To add a key value pair, we go inside the resource type amount dictionary, inside our dictionary, and we call the add function. Over here we need to pass in the key and the value. So let's pass in resource type, let's say stone, then for the value let's say 56. So if this is going to add the key stone onto our dictionary, and it's going to link the value 56 with that stone. This is how we can add a value, and then for reading a value, we do it pretty much as if it were an array. So we use the square brackets, and inside here we put the type for our key. So in this case, our resource type dot stone. So if we do a console.writeLine on this one, let's see. And yep, it does print 56. Okay, great. Now one key point about dictionaries is that the key itself, this one must be unique. So if we try adding a value on the same stored key, if we try adding some kind of value, nope, right away we have an error. An item with the same key already has been added. So remember that each key must be unique. If you want to update the value, we can just access it, so as if it were an array, and then set it to something, and yep, this will work. Now when getting a value, if we try getting a value that does not exist, so if we try going to this, on the resource type dot wood, if we try doing a console.writeLine on this one, yep, here we have another error, key not found exception. The given key was not present in the dictionary. So if you don't know whether a certain value exists, you have two options. First, you can just check to see if it contains that key. So access the dictionary and call contains key, then pass in the key. So this will return true or false if this key exists inside the dictionary or not. That's one approach, and the other one is to access the dictionary and call try get value. This one, like the name implies, tries to get some kind of value for some key. So the first parameter is going to be the key. So let's say resource type dot wood. And then the second parameter, this is the first time that we're seeing this. This one is not just an int value parameter, it is an out int. This means that it's an output parameter. This is a more advanced topic that I cover in detail in the advanced section. For now, just know that this is an output parameter. So this function is basically going to return bool, so it is going to return true or false. True if the dictionary has this key, and false if it does not. And if it does have, then it's going to output whatever it is in here. So let's define a variable for the wood amount. So if it does have wood, then it's going to store the amount on that one. So then we can see if this one does have this value. If so, then let's print out the wood amount. Except we didn't add, so this should not run. And if there it is, that doesn't run. But if over here, instead of assigning stone, let's assign it to wood. And if there it is, now it does run. Again, if you're not familiar with this output syntax, don't worry about it. I'm going to cover it in more detail in a later lecture. If you do use it, just know that it has this syntax. Also, like we saw, we can modify values, so we can go inside this, resource type.wood, and set it to something to modify it, so this works. But this also works for simply adding values. So instead of calling .add, you can just do it like this. And if it does work and does add that value. And of course, since we can add values, we can also remove them. So we can call remove and then pass in some type of key. So let's say resource.wood. So this should remove the key, so then this code should not run. And if there it is, doesn't run. So here we are creating a dictionary, and then afterwards on a separate line, we are assigning values. But like we have with arrays and class and so on, we can also initialize the object directly when we create it. The way we do that is we open and close the curly braces. So the same as we do to initialize some kind of array or list. And then inside it, we put whatever elements we want to initialize inside this dictionary. But remember, dictionary is a key value pair, so we need to somehow define a key and a value pair over here. If we just do resource type.stone and then 10, if we just do this, nope, this is an error. The correct way to define a key value pair is with another pair of curly braces. So put this one inside open and close just like this. And then if we want to initialize more, we can just start with wood and something and so on. Now importantly here, pay close attention to the syntax. So we've got curly braces on the whole dictionary, and then again for each individual key value pair. Now one common thing you're going to do with dictionaries is simply cycling through them. For that we can just do a for each directly on our resource type dictionary. And for this one, the iterator variable will be a type key value pair. Simple like this, and then inside this one, we can access the key or the value. So let's do a console.writeLine, this one .key, then let's do a colon and key value.value. Let's get rid of this code and let's test. And if there it is, cycles through the entire dictionary and prints out stone and then the amount. Alternatively, instead of cycling through the dictionary itself, inside of here we've got a keys collection. And this is just basically going to scroll through every single one of the keys. So over here you would have just resource type. This would be the key, and then you could simply access and print out the resource type, and then go inside the dictionary on this type to see the amount. And if there it is, same result. So this is the other type for each. And also finally, you can also cycle through just the values. And on all of this, always remember that these are really just key value pairs, meaning it's up to you to define what value you want to use for the key and the value. It does not have to be just simple types like ints and enums. For example, the key can be some kind of player class and the value can be some kind of weapon class. That would be perfectly fine. So just remember that it doesn't have to be just simple types. You can use whatever type you want for the key and the value. Now here's a bonus tip specific to Unity. Let's say you want to build some kind of resource manager, something like this. So you have a resource manager class, and inside you've got a dictionary, you have resource type and an int. But then you want it to be preset with some amount that you want to set in the editor. But the issue with dictionaries is that Unity does not serialize them. So even if we add serialized field private, even if we do this, here in the editor, nope, we do not see it. The resource manager has no fields. Nothing shows up in the editor. So instead, here's a neat trick you can do. You can create a custom class, and on that class, you basically use the key value pair. So here I've got a resource type and an int amount. Now importantly, we need to mark this type as serializable in order to show up in the editor. And if we do, and then we just make a list of this type, if so, then yep, this one does now show up over here in the editor. So we can set it to something, and then we have all of our elements of our custom type, so we can set all of them to whatever we want. So there it is, all the various values, all the various keys. And then on this same script, over here on the awake, we just create the dictionary. We cycle through the list that we exposed in the editor, and we just go inside the dictionary on that type and set it to that amount. Then we can just print out the content of the dictionary, and up here in the console, we can indeed see, yep, we did create the dictionary, and we did initialize it with our data. Alright, so that's the dictionary. It's a super useful data type, really helpful when you have two pieces of data that can be connected like a key value pair. So this is absolutely essential in things like resource management or linking any kind of data together with one another. Hello and welcome, I'm your Code Monkey. In this lecture we're going to learn about some other collection types like queues, tags, and a bunch more. Okay, so in the beginner section we already learned about arrays and lists. Then in the last lecture we learned about dictionaries. Honestly, those are really the only collections that I normally use myself, but there's still a bunch more that can be useful in certain scenarios, so here let's see them. One simple one is called the stack. Think of it like a stack of papers. You can place papers on top, so you can push them. And for grabbing a paper, you can only grab the one that is on the top. In this case on the stack, grabbing simply means pop. So you can push and pop elements. This is what is called a first in, last out collection, or also known as follow. Here in the code, the way we do it is super simple. We just create a new stack. This one takes a generic type, so similar to the list. So let's say a stack of strings. Let's call it name stack, and we construct it. And then on this one, we can call the function push in order to push values onto the stack. So let's push the string CodeMonkey, then let's push the string for Iron Man, and let's push the one for Spider-Man. Okay, so with that, we push them. And now if we go into the stack and we call pop, this one is going to remove and return the object on top of the stack. So like I said, this is a follow collection, meaning first in, last out. So ask yourself, what do you think this will return? This is the first element that is added, so technically this is going to be the last one out. So let's do a console.writeLine on this. Okay, let's see what this returns. And you're correct, this does return Spider-Man. Like I said, first in, last out. So we first put CodeMonkey, so this means this is going to be the last element that we're going to grab. And when we pop, we're going to grab the one that we last put on there, which is going to be this one. And eventually, if we don't put up anything, so if we comment out all of this and we try doing a pop, yep, here we have an error, the stack is empty. So to avoid that, we can use try pop, which will try to get an element if it exists. And if you want to just look at the last element without removing it, we can call peek. Okay, so that's a stack. Another related collection is the queue. This one, the easiest way to visualize is some kind of queue of people. So the first person that gets added onto the queue is going to be the first one that gets out. So this one is a FIFO collection, first in, first out. The way we build it is pretty much the same as a stack, except this one is a queue. So then let's make a queue of string. So for the string queue, and let's construct it, so a new one and build it. Then on the string queue, in order to add elements, we call inQueue. So again, same thing, let's add in CodeMonkey, then Iron Man, and finally Spider-Man. Okay, so we queue all of those, and now on the string queue, we call dequeue in order to grab the element. This one, again, like the pop that we saw previously, this one removes and returns the object. So if we do a console.writeLine on this one, again, queue is FIFO, first in, first out, so let's see what this one returns. And if this one returns CodeMonkey, which was the first element that we added. So some practical examples. A queue can be useful in something like a tycoon game, where you have literally a queue of people. Like for example in my own game, Battle Royale Tycoon, when there's a queue to join each arena. And for the stack, a great practical example is how this can be very useful for making some kind of undo system. So maybe something like a city builder. You can push onto the stack the action to place a building somewhere, and then to make an undo, you simply revert that action, which would eventually demolish that building. Now importantly, you always want to do it based on the last building that was built and not the first one. So these two collections definitely have their own use cases, although like I said, normally I just use lists. I've built both these systems, like a queue for a tycoon game and an undo kind system. I've built both of these using just lists. Remember how on a list you can access the list on index 0 and call remove at to remove it from a certain index, so similar to a queue. Or you can also just access it, the last element on the index, the last element on the list, similar to a stack. So personally, I normally do all this custom logic using lists, but if you like, these two collections can be quite useful, so just remember they do exist. Next collection is what is called a hash set. This one allows you to store a set of elements, so let's make a hash set of string. So for the string hash set, let's construct it, then go in the string hash set, and this one we call add to add elements, so for example add the element CodeMonkey. And yep, this one does work. However, one important thing about this type, the hash set, the important thing is that all elements have to be unique. So like this it works, but if I duplicate it, and now I do a console.writeLine, and let's print out the string hash set.count in order to count all the elements. So we're adding 2 elements and then counting it, so let's see what this returns. And if this one returns a 1, because again we added a duplicate element, so it actually didn't add it. So you can add elements, you can remove elements, and you can also do a union to combine multiple hash sets. So the hash set can be useful for some kind of elements where you always want it to be unique, so maybe a player ID. So for those kinds of use cases, it can be a useful collection. The next one, we have the sorted list. This one, pretty simple. Like the name implies, this is the same as a regular list, but it gets sorted automatically. So you can make a sorted list of int. Another collection is a sorted set. So this one, pretty simple, same thing. It records a set of elements, and it is constantly maintained in a sorted order. Alternatively, you also have a sorted list. This one has a key value pair. Then you have the sorted dictionary and so on. So there's a bunch of collections that serve various purposes. Like I said, personally, I really just stick with arrays, lists, and dictionaries. I normally don't use any of these, but it is good to know that the language can do all these things by default. Maybe you have some use case for which the queue is perfect, so definitely make sure you know these collections exist. Hello and welcome, I'm your CodeMonkey. In this lecture, we're going to learn about the params keyword that we can use in a function, which then allows us to call it with any number of parameters. Okay, so let's make a function to see it. So let's make a private static void. Let's call it print player name and receive a string for the player name. Then over here, just a console.writeLine on the player name. So that's it, super simple, just a regular function like any other. And up here we can call it with CodeMonkey. And if it does work, it does print, great. But now let's say that I want to support 2 player names. I want both of them. I want support for both 1 player name and 2 player names. So in order to do that, I need to copy paste this and make another one with player name and then player name 2. So yep, this works, but now I have 2 functions, one with 1 parameter and one with 2 parameters. And now let's say I want to support 3 parameters. So again, I need to make another function, duplicate a ton of code and so on. So right away you can see the issue. This is basically the problem that param solves. So for that, let's make just 1 function. And up here, let's call it with 2 parameters. And right now, yep, we have an error because this one can only take 1 parameter. So now here for the parameter, let's write the keyword params. We write params and then we write the type for the parameter. And in order to use it with params, this type needs to be an array. So let's make a string array. And for the player name array. And up here, let's just do a console.writeLine on this one .length, just to see how many we call. And right away, we can see we have no errors up here. So calling this function with 2 parameters does work. Let's run it. And up it prints out 2. And now let's call this function with just 1 parameter. And again, no errors. And yep, now it prints out with 1. Also, if we pass in with no parameters, and yep, we do have an empty array. So yep, that's it, super simple. You can just add the params keyword, and that way now we support any number of parameters. This only has 2 requirements. The first one is that the type over here needs to be an array. For example, if you make string, it does not work. If we make it just string, then no, it does not work. If we make an array of multiple dimensions, this one also does not work. So it needs to be an array of some type. It can be string, it can be int, it can be pretty much anything. And the second requirement is that this one needs to come at the end. So afterwards, if we define an int age, nope, does not work. Here we have an error. And the error says here a params parameter must be the last parameter in a parameter list. So if we want to combine a params along with regular parameters, we need to make sure the regular ones come before and the params comes after. This way now, yep, up here we can type in an int and then any number of strings. And yep, all of this does work. That's it, really simple and sometimes quite useful. So anytime you have some function where you would like to receive any number of parameters, whenever that happens, always remember to use the params keyword. Hello and welcome, I'm your CodeMonkey. In this lecture, we're going to learn about how we can use optional parameters in a function, meaning parameters that we are not required to use. Okay, so here is a normal regular function. It supposedly spawns some kind of unit. So it takes a spawn position, the type of the unit, the spawn rotation, and some kind of health amount. And then to call this function, we call it as usual. So we call it and pass in all of our parameters. If we run this, if it works, spawning unit of type melee with health 56 on this position, this rotation. But now let's say we want to spawn a ton of units and we don't want to be forced to pass in all of these parameters, especially for example, if some of them are going to be defaulting to some amount that is going to be copy pasted all the time. Let's say for example, the only thing we want to care about is the spawn position, and then it will default to all the other ones. So one option would be to simply make another version of this function. So let's make another one and let's make another version that only takes a spawn position. And then in turn, that one calls the other version, passes in the spawn position, and then passes in defaults for all the other ones. So let's say melee, quaternion.identity in order to have the regular rotation, and let's say 100 health amount. So we can do this and now do this and spawn on new vector 3 of 10, 5, 0, something like this. And if there it is, we have no error. And running the code, yep, it did work. It did use those defaults and the 1050 position. So this works. This is one valid option. But we have another option where we don't need to define multiple functions. We can simply use optional parameters. To use them, it's really simple. So we just have our function with our parameters. And then after the parameter, we simply write an equals and then assign some kind of default value. So for example, for the health amount, let's default it to 100. And now up here, when calling this function, we need to include all the other parameters. So for this one, let's include the unit type and let's include a quaternion rotation. But now we don't have to include a health amount. So like that, this one has no health amount. And if we run, yep, the health amount defaults to that 100 default. So it's really this simple. You just add equals and then some kind of default value. We just have a few simple rules for how we can use this. First is how the optional parameters, these have to appear after the mandatory parameters. So for example, if here on the unit type before the quaternion, if on this one I define an optional parameter like this, nope, here we have an error. It is saying optional parameters must appear after all the required parameters. Then another rule simply has to do with default values. Also, by the way, like I mentioned in the beginner section, the compiler doesn't really care about new lines. So if you have something with tons of parameters, you can just place them all in a new line, and that way it becomes a little bit easier to read. So like this. Okay, so like I said, the second rule simply has to do with default values. And the rule is how default values need to exist at compile time. So here we cannot construct an object. We cannot do new quaternion and then construct a new quaternion with something. Nope, this does not work. Like it says here, default parameter for value spawn rotation must be a compile time constant. So we cannot do this, but we can use, for example, the quaternion.identity. This is a constant, and yep. So we cannot use that, but we can use the default keyword. This will basically use the default value for that type. So in the case of a quaternion, which is a struct, it is simply going to initialize that struct with everything at 0. So for this struct, we can use this. And for the vector3, same thing, we can use that. And for the unit type, this one is an enum, so we can just assign a default value. And if like this and everything works. Alternatively, we can also use constants, which is something that we're going to cover in a few lectures. So you can define a constant, and then you can definitely use that constant as a default value. So optional parameters need to have certain defaults in order to work. And then over here for passing in the parameters, since we marked all of those as defaults, we can call it just like this. And yep, the code runs, it works, and it works with all the defaults. Then alternatively, we can pass them in one by one. So for example, if we want a spawn position, let's put some kind of spawn position. And then for the unit type, let's say we want like this. So yep, we just assigned 2 parameters, and yep, it did work. But now let's say that the only parameter that I want to assign is just the health amount. So for that, I go up here and I just write some kind of int, so just 56. And nope, this one obviously has an error because argument 1, it expects a vector3, not an int. So just like this, you need to pass in all the parameters in order. However, you can actually pass them without being in order. And for that, we really just need to write the name of the parameter. So in this case, the parameter is the health amount. So we write that and then a colon. And yep, just like this, it does work. This is basically calling the function and assigning the health amount parameter to this value. And on the other one, since we didn't assign them, these remain the defaults. And if you're running the code, we do see with health of 56. Also, by using the same method, we can pass in parameters in any order you want. So for example, the health amount, then let's pass in the unit type. So unit type and unit type dot something. And yep, this is definitely valid code. As long as I write the name of the parameters and then a colon, then give it a value, everything does work. Alright, so that's optional parameters. It's quite a useful feature to help you avoid having tons of function versions for all kinds of parameter combinations. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn something very important, the difference between value types and reference types. If you don't know the difference, then at some point in the future you will go crazy because you think something is behaving as a reference when it's behaving as a copy. So in C# you have several types, and mainly they are either value types or reference types. Reference types, they store references to their underlying data, whereas value types, they contain that data directly. Some examples of value types are the symbol types like int, float, bool, and so on. These are all value types. And for reference types, these are things like class, object, arrays, and strings. However, importantly, struct is a value type. We're going to cover structs in detail in the next lecture. They look similar to classes, but this is the one big difference between them. Structs are value types and classes are reference types. And over here, as you can see, arrays are reference types. Even if the underlying data, if you're making an array of ints by themselves are value types, but if you make an array of int, the array is going to be a reference type. And then strings are a bit of a special use case in that they are technically reference types, but in some cases they behave like value types. So the big difference is shown down here. With reference types, you can have multiple variables, and you can have all those variables, all of them pointing to the same underlying object. Whereas with value types, any variable you make with some kind of value, if you then assign that variable to another variable, you are making a copy instead of a reference to the original value. Another difference is how reference types can be null, whereas value types cannot. So for example, if you have some kind of enum for your weapon types, if the player does not have any weapon, you cannot set it to null. Enums cannot be null, neither can ints, floats, bools, and so on. So here let's see some code. First, let's define an int, which is a simple value type. Okay, very basic, just the variable named a and contains the value 7. But now let's make some kind of class which is going to work as a reference type. So here let's make a class, call it my class, and inside let's just expose an int a, okay? And now up here, let's create a new my class. So my class equals a new my class, and then let's go inside that one and set the a to some kind of value, let's say 7. And then let's make another my class, call it my second class. And now let's assign this one to the my class. And over here we go inside the my second class and modify a to a different value. So here now we have 2 different variables. We're initializing the first one like this, then we're assigning it to the second variable, and then we're modifying the value inside of the second variable. So if we print out over here the my class.a, what do you think this will say? So let's do a console.writeLine and print this out. Let's see if it says 7 or 5. And if there it is, it does say 5. Again, that is because classes are reference types, so over here, even though we have 2 separate variables, they are both pointing to the same underlying class. So they're both pointing to the same underlying memory position, they're both pointing the same actual object, both of them are referencing just a single instance of our my class. So by going through either of these, we're actually modifying the same underlying object. we do not have two objects, we have just one and two references to that same object. So when we modify this one, we're not modifying it just on this second object, but since this one has the same reference as this one, both of them are modifying the actual underlying object. So by modifying either of them, we are modifying the same underlying object. Now let's look at this exact same example, but using our ints, which are value types. So you've got an int a of 7, then let's define an int b and let's assign it to the value of a. And then let's go inside b and set b to something else. Let's put it on 5. And now let's do a console.writeLine on a. And let's see what this one prints. So will it print 7 or 5? And if there it is, the result is 7. Again, this is because int is a value type and not a reference type. So over here, we're defining a variable a and assigning the value 7. And then we're assigning b, and then we're defining b and assigning it to the value of a. But again, since a is a value type, this is going to essentially copy the data that is currently stored inside a. So after this point, we have two variables, and each of them holds a copy of their data. And then over here, when we modify b, that is only modifying the copy that was created in here and not modifying the original data that we have in here. This is the one big difference between value types and reference types, is how up here we are working with a reference and we have two references that both of them point to the same underlying object, whereas down here we have copies. So we have one copy here, one copy there, and by modifying the second copy, this has no relation to the original data. Now, the scenario that is most important to know this difference is when working with structs, which we're going to cover in detail in the next lecture. For now, don't worry too much about what they are. I just wanted you to see the difference. So a struct is made pretty much the same way as a class. We just change the keyword into struct, and let's name this my struct. So like this, and up here we can write literally the exact same code, but write it with a struct instead of our class. So up here, use my struct, then over here, this one is my struct, and my second struct, and then we modify this one here, and we print out the my struct.a. Okay, so here's our test. Literally, we have the same code down here as we have up here. The only difference is one code is working with a class, another one is working with a struct. So let's see the difference between these two. And yep, with the exact same code, we have two different results. That is exactly because of the difference between value types and reference types. The class has a value of 5 and the struct has a value of 7. That is because the class up here, again, both of these are referencing the same underlying object. So when we modify the second one, we're both modifying the same underlying object. So when we print out the data stored in the first one, again, same object, so this one prints out 5. And yep, we do have 5. And then down here, when working with structs, structs are value types. So over here, we create a brand new struct. But then on the second one, when we assign it, we're actually creating a copy of the data. So now this one has a completely separate copy that has no relation, no reference to the original data, to the original my struct. So when we modify this one, we're only modifying this copy and not touching this one at all. So that is why on the struct, the result is 7, which is the original value that we set over here, because when we modify this, we're only modifying this copy and have no relation to this original data. Now, this difference between value and reference types is also very important in functions. For example, private static void my function. Let's do some kind of test function. And here, let's receive of type my class, another one of type my struct. Then let's just go inside and put it on something. So my class and my struct. Let's modify to do the exact same test as previously. Let's just comment out this testing code. And then over here, let's create a my class. My class, let's create a brand new one. And let's put my class, set the a to 7, and create a new struct. We also set it at 7. So both of them have the same value in their a field. And then we call my function, pass in our my class and our my struct. And then let's do a console.writeLine on the my class.a, then some space and my struct.a. Okay, so again, let's see what happens. And yep, there it is. My class has a value of 5 and my struct has a value of 7. Again, that's the same difference between value types and reference types. It's how when we call this function and we pass in our values, the class is going to be passed in as a reference. So as we modify this one, we're actually modifying the reference. So we're modifying the underlying object that was sent into this function. Whereas for the struct, the function receives a copy of the data. So the copy that we receive over here inside the function, this has no relation to the actual data defined up here. So whilst inside this function, modifying this class modifies the actual data outside of it, but modifying this struct only modifies a local copy. Also, what I mentioned a while ago about how arrays are reference types. So for example, let's do another test. So let's make our function, take in some kind of int, and then an int array. Then over here, let's modify the value of a. And let's go inside the int array on index 0, and let's modify the value. Okay, so now up here, let's define some kind of int, and let's define an int array. Let's construct an int array and just put a value on there. Okay, so now we call my function, pass in a and the int array, and now let's do a console.writeLine let's print out the A, and then print out the int array on index 0. Okay, so again, let's see what this does. And if there it is, same thing. The int was not modified inside the function, but the array was. That is because ints are value types, so this one is passed in as a copy, but int arrays, these are reference types. So when we pass in an int array onto our function, we're passing in a reference to the original data. So when we modify this inside the function, we're modifying the actual original data. And also, since we're on the topic of value types and reference types, I mentioned a while ago how value types cannot be null, so you cannot define an int b equals null. So this is not possible. We have an error, cannot convert null into int because it is a non-nullable value type. However, if you really want to do this, you can do it. Instead, you just have to use a custom type called nullable. And with this, you can make any value type like ints, bools, floats, and so on. You can make any of those into nulls. And this is something that can sometimes be useful. I cover nullable in detail in a lecture in the advanced section. Okay, so that's the differences between value types and reference types. Be very, very careful with this difference. It might sound like I repeated myself way too much during this lecture, but that's because this is really so important. Always keep in mind whether you are working with a copy or a reference. One of the most important ways to see this difference in action is in the difference between classes and structs. So let's learn about structs in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn all about structs. These are structures of data that are similar to classes, but also a little bit different. Okay, so structs, like I said, are pretty similar to classes in how you define them. You'll literally just swap class for struct. So for here, for example, let's make a class named player. Right now, this is a class, and just by swapping this into struct, yep, now this one is a struct. So that's it, super simple. However, just doing this has some really important implications. The main one is how classes are reference types and structs are value types, which is what we covered in the last lecture. This means that when you use something as a class, like a class parameter, it gets passed in as a reference, whereas with a struct, it gets passed in as a copy. So here we can do a simple quick test, make a player struct and a player class. Then just run this code, just making the usual start function, because over here I'm working in Unity. Let's make a private void test function struct, and another one test function class. Okay, so here is some code. We create a new struct and new class, and we assign a field inside of them to the value 1. Then we have two functions, and these functions, these do the same thing. So they just set that field into 2. And then we do a log. So let's see whether this one keeps the number 1 or whether it keeps the number 2. And yep, like the log says here, the struct keeps the number 1, whereas the class keeps the number 2. Again, that is because struct is a value type, meaning these are passed in as a copy. So over here we are modifying the copy and not the original data. But classes are reference types, so when we modify a class inside a function, it modifies the actual position in memory, the actual original object. So the reference type gets changed, but the value type does not get changed. This difference is really extremely important, so I truly hope you fully understood everything in the previous lecture. If not, go back to it and rewatch it. It is really important so you don't get confused like I did many times before I memorized this. This is one of the main differences between structs and classes, how classes are reference types and structs are value types. In general, structs are mainly used as just data containers meant to organize your data. The simplest example is really just the vector3 type inside of Unity. So we can inspect this one, so let's right click and go to the definition. And yep, over here we do see this is a struct, and it's a struct that pretty much just holds 3 components, so x, y, and z. So rather than having 3 separate fields whenever we want some kind of position, we just make a struct that in itself has these 3 fields. Whenever we have several pieces of data that all of them make up one logical unit, then perhaps consider making that a struct. However, again, remember how it's a value type. For example, in Unity, you cannot even directly modify one of those components. So if I set the position .5 equals something, if I do this, nope, it does not work. Now, technically, this is more related to the fact that this position is actually a property and not a variable. But still, the reason why it's a property is because it actually copies the data and sends it over to the backend of the engine itself. So in Unity, when you need to modify something, you need to assign it to a new vector3. So basically, you need to give it another copy of another piece of data in order to actually modify it. So usually, structs are used in an immutable manner, meaning they never change. Once you create a struct with a certain value, usually you keep it at that value. However, that is not an absolute requirement. It's really just a good convention to follow. For example, the vector3 struct, so let's do a position, define it as something, 10, 21, something. And like this struct inside actually contains the normalized function. And if we do this and then do a debug.log on this position, let's see. Yep, this function does indeed modify the underlying data. So in theory, structs can indeed be mutable, they can change, but in order to avoid confusion, you should probably avoid this as much as possible. You should probably always treat your structs as immutable. Just following that one simple rule will make things much simpler to understand. Now, structs, like classes, they can have fields. They can also have functions, like we saw here, to normalize. and they can even have properties. One big difference is how they cannot inherit. I talk about inheritance in more detail in the next lecture, but basically with a class you can make it inherit another class. So public class, base class, and then public class for some kind of unit class, and this one can extend base class. So this works, this is valid code. But over here on this player struct, if we try extending base class, nope, an error, structs cannot extend classes. The one thing they can do is actually what this error message is telling us. They can indeed implement interfaces. I will also cover interface in detail in a few lectures. Then structs can also have constructors, just like classes. However, in most C# versions, you cannot have a parameterless constructor. So over here, public player, just like this with no parameters. And nope, we have an error. So as you can see, parameterless struct constructor is not available in C# 9, but if you're using another version, this is possible. Instead of defining it yourself, it always has one by default. So up here we can do new player, and yep, this works. So for the constructors, if we define any of them, it has to have some kind of parameter. So usually on the constructor, you add some kind of thing to initialize the actual struct itself. And then one common error with constructors is this one right here, which is all of the elements, all the fields must be fully assigned before control is returned to the caller. So if we define a constructor like this, we must initialize all the fields. So over here, this .a equals a, and yep, now it does work. So every constructor you make has to initialize every single field within that struct. Again, this has to do with difference between value types and reference types. As soon as you define something of struct type, like for example some kind of variable, like a kind of player variable like this, as soon as you define it like this, if you define it like this, it's an error because it is uninitialized. But we can initialize it. We can just use default. This is a keyword that pretty much returns the default of whatever type we have. So if we do it like this, let's see what this says. And yep, the default of a struct is indeed a struct. And then we can even go inside of it. So let's print out the A. And yep, so it creates a struct and initialize the variables, all of them at 0. So that's what default does, initialize everything with a 0 value. However, if we now make this into a class, and if there it is, default value for a class is null, and since it's null, that means it has no object, so we cannot access anything inside of it. Again, goes back to the difference between value types and reference types. Reference types by default are null, whereas value types, they always have some kind of value. So when you make a struct, you can create a new struct like we saw by using the default parameterless constructor, or we can use any custom constructors, or we can just make the struct and over here define any kind of thing, so a equals 2. And yep, this is valid code for initializing a struct. One more important thing about structs is, once again, how they are related to value types and not reference types. So one big difference is how they are stored in the stack instead of the heap. These are two different positions in memory. One is much more efficient than another. I actually have a nice story about this. In my first Steam game, Survivor Squad, for the implementation of the Fog of War, the world basically has a ton of tiny quads on top. Then as the player sees some area, those quads are marked as invisible and they are not rendered. So each of those tiny quads needs a little bit of data in order to know the position and know whether it's visible or not. In the first version of this system, I sorted that as a class and it was terribly slow, and then I literally just swapped class for struct and suddenly got a massive speed boost. All because of how structs are very efficiently stored in memory. So in general, use structs to hold different pieces of data together. And in general, you should use them as immutable pieces of data, meaning they should not change, and consider using them when you have some kind of memory performance issues. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn some intermediate topics related to classes, things like inheritance, polymorphism, protected, override, and a bunch more. Okay, so in the basics section, we already learned the absolute basics of classes, how we can define a class which has fields, properties, and functions, and then you can create instances of that class. So that's the basics, but of course classes can do so much more. One of the main things they can do is simply the concept of inheritance. That is how you can have one class that inherits something from some other base class. For example, let's say we have this general unit class, meaning this represents any kind of unit in our game, and all the units are going to have some kind of speed and some kind of move function. And then we can have the player, and the player is a type of unit. And to define that relationship, we can make the player class extend the unit base class. That means that the player is going to inherit everything from this unit class. So on the player class itself, we are not defining any speed field or any move function. Instead, just by making it extend the base class, it is going to inherit all of these elements. Essentially, the player class, this one contains everything inside player and everything inside unit. Then we can have another enemy class, which again is also meant to be some kind of unit, so we also extend the same unit base class. And again, this one is going to inherit everything. So the enemy class itself is also going to have a speed, move function, and so on. So anytime we have some common logic that belongs to any kind of unit, we just need to add it onto the unit class itself, and anything that inherits from that unit class, any of those classes are going to automatically receive the new code that we add to our unit. And then each of the classes that inherit from base class, each of those can also have code themselves that is unrelated to the base class. So for example, the player can have some kind of move player function, and the enemy can have some kind of enemy health field. These only belong to these classes and do not belong to the base class. So for example, the enemy has no relation to the player move player, and the player has no relation to the enemy health. So always keep in mind that the inheritance does not go both ways, meaning the above unit, this one over here, has no knowledge that there is a player extending it and the player has this kind of function. So the player inherits everything from unit, but unit does not know anything about player or enemy. Okay, so let's see the syntax. Here is the basic unit class. We've got a speed field and a move function. And now let's make it clear, so let's make a player class. And now in order to make this one extend our unit class, for that, after the player class name, after that we write a colon, and then the name of the class that we want to extend, so in this case, unit. And if that's it, just like this, the player is going to be extending the unit class. If we write any code inside of here, we can already access the unit fields. So for example, let's make a constructor, so a public player constructor. And over here we can access, we can access the field, we can set it to something, and we can call move function. That does work. So even though speed and move are not defined over here in the player itself, since the player extends unit, it also inherits all of this. But then, like I said, inheritance does not go both ways. So up here on this one, let's make one for the move player. Let's make some kind of move player function. And now down here on the unit script, if we try calling that, nope, that does not work. The unit does not know anything named move player. This function only exists on the player class itself. Now, another thing we can do is override some base function. So for testing, let's actually go up here. Let's create a new unit. So let's build a new unit and a new player. Okay, so we have these. And if we call the move function, and on the player, let's call the same move function. So if we run this, it should print this line twice. And if that's correct, it only printed 3 times because I included it over here in the constructor. But yep, it did work. So now, like I said, we can override some base function. So for that, over here on the move function, let's add the keyword virtual, and now we can go onto the player, and on the player, let's define a function exactly like this one. So let's define one just like this, and inside let's say move player. And if we do it just like this, we actually see this green squiggly line, and we can check. And if this is basically telling us that this one is hiding the inherited member, and if we want to override the implementation, we can add the override keyword or add the new keyword if we want a new function. But nope, we do want to override that one. So on the base class, we add the virtual keyword, and on this one, we add the override keyword. And yep, so now like this, using this code, so the unit has this one, it's a virtual function, and this one is overriding that function with a different message. So we have 2 different messages, and up here we are creating a unit, creating a player, and then calling the same move function on both of them. So now let's see what this prints. And if there it is, so when we call move on a unit, it is running move unit, but when calling the same move function on a player, it is actually running the overridden logic. So this is how you can extend some base class, so make it inherit from something else, and then override certain functions to have different behavior from the base class. Now, this is also a great time for me to mention how you can override the toString function. Basically, every single class in C# is always going to extend the base object class, and that base object class always has a toString function. So for example, up here, we did not define any kind of toString in here, but we can call toString. Yep, this does work. As you can see, this exists in the object base class. This is the main way of how any single object, any single type can be converted onto a string. We can do a console.writeLine, and we can print out, for example, player. And yep, this does work because this one is going to automatically call toString in order to convert the player onto a string. So anyways, yep, all objects have this function implemented automatically. However, if we run this, yep, the player just says, essentially just prints out the actual name for the type. So we're inside the namespace C# course, we're inside the program class, so that's the program class up here, and then inside the player type. So sometimes printing this is not very useful, but the toString function, this one is also marked as virtual, which means we can also override it. So let's do the same thing. Let's do public override, and automatically this one already shows us some code hints. So let's override the toString function, and it's like this, so it returns a string and is called toString. And over here, we just return the string that we want to name our player. So for example, let's give the player some kind of name. So let's give it a string for the player name. And let's receive this string over here. So we've got a string for the player name and set this.player name equals this. And then down here, let's print out player and then the player name. Okay, so we do this, and up here, let's print the name as CodeMonkey. And then we do the same thing. So let's do a console.writeLine, and let's just put player. So not even any toString, so just like this. Let's see what this does. And if there you go, now we have overridden that behavior, so we can now say whatever message we want from our custom type. Okay, great. So with this, we can inherit from a base class, and we can override some functions. And of course, what I'm saying here applies to any class you want to extend. You can have as many classes extending a base class as you want. So for example, we can make a class for an enemy, and also make the enemy also extend our unit. And for example, on this one, we can also override the exact same move function. So we can do this. This one is move enemy. And now up here, let's do the same testing code, enemy, enemy, and let's construct a brand new enemy. And then we call enemy.move, and let's see what this runs. And if they're going like that. So move unit, move player, move enemy, even though over here we are always calling the exact same function. So basically we have 3 implementations of this, and each of them is slightly different because they're overriding the base implementation. Basically the only rule with inheritance is how you can only inherit once. You can only extend a single base class. So if over here we were to define a unit2, okay, here's a completely separate class, and over here let's try to extend that one as well, and nope, we have an error. It is telling us that enemy cannot have multiple base classes, so we can only ever inherit from a single base class. If you want to achieve something similar to that kind of result, for that we have interfaces, which we're going to cover later on in a future lecture. But you can definitely go the other way as deep as you want. So over here, for example, we have enemy, which in turn extends the unit class. Then we can go one step further, so let's have another class, for example, the enemy melee, and let's have this one extend enemy. And yep, this does work. Then we could have another one for the enemy melee boss, something like this. So for some kind of boss that also extends melee, this one extends enemy melee, just like this. And yep, all of this is valid code. However, just like this, you can probably already tell how this can become quite confusing quite quickly. So over here, let me point out that inheritance is a tool that can be very powerful, but also can be very easily abused to the point where it's much worse than not using it. There's a common programming joke that goes, basically you wanted a banana, so you construct a banana but end up with an entire jungle. That's because the banana class would extend the fruit class, which in turn would extend the tree class, which requires a jungle class, and so on. So if you have complex, really deep inheritance structures, if you have that, you can end up with some really messy code. One common saying to counteract this is prefer composition over inheritance. This is how you can, instead of having a complex web of inheritance, instead of that, you can compose your complex objects based on separate components that make up the final object. Now, this is a more advanced topic, so don't worry too much if you're not fully understanding everything that I'm saying here. I'm only saying this just in case you are curious and want to research further on this topic. If you want, you can Google composition versus inheritance, and you will get a ton of really interesting results. The only thing I want you to take away right now is just remember to be very careful when you're using inheritance. Always ask yourself if you absolutely need it. Sometimes you do, but many times chances are there's a better way to achieve the same result in a much easier way that does not become insanely complex. But inheritance does have its place, so let's learn a little bit more about it. One extremely crucial thing that is not related specifically to just inheritance is the concept of polymorphism. This is how you can treat an object as a different type of the object as long as those types are related. So for example, up here, if we define a field of type player, so we have this field, and we can assign this to the player that we created. Yep, this does work. However, we cannot assign our enemy object over here. That is because you cannot implicitly convert our enemy into a player. Because again, going back to the diagram, even though they share the same base class, they by themselves are two completely separate types. However, now let's make a field of type unit. So we have a unit, and obviously for this one we can assign our unit type. Yep, this does work. And on this one we can also assign the player type. Yep, this also does work, because again, player extends unit, so it can be used in place of a unit. And same thing for the enemy object. Yep, this one also does work. And now if we go into this unit2 and call the move function, let's see what this runs. And if there it is, this one runs the move enemy. That is because even though we assigned this to a unit variable, even though we did, the object itself is still an enemy object. So the object itself, the type itself, that one is still overriding our base move function. And for example, if we assign this to player, yep, this does work. But like we saw on the player itself, let's define a public void move player. So let's define this function that only exists on the player type. So we did this. And if we go over here onto player and call move player, yep, this does work. This is valid code. However, if we go through the unit and call move player, and nope, that does not work. It does not exist. That is because again, this field, this one is now of type unit, even though the object itself is of type player. Since we're accessing it of type unit, we can only access the things that unit itself has. So for example, one fun thing you can do with this kind of property is, for example, having a list of units for some kind of unit list. You can do this, and now inside of here, we can place a unit, we can place a player, and we can place an enemy. And yep, this works. It works because our player class and our enemy class, those extend our unit base class, so they can all be cast down into a unit type. Now, like I said, the concept of polymorphism, which is basically using one type as a different type, that concept is not specific to inheritance. For example, it also works with interface, which we're going to see in the next lecture. If we have some kind of function that requires a player-specific type, if so, then we need to receive some kind of parameter specifically as type player, but we can do a bunch of logic that works on just units, and that logic will work on units, it won't work on players, enemies, and anything else that extends our unit-based class. And now that we are looking at inheritance, we can also look at a different access modifier. So far, we've pretty much just been using public and private. Private means that only this class can access it, and public means that anything else can access. But when it comes to inheritance, we have another super useful one, and that is protected. For example, let's go down into our unit. And for example, over here for the speed, instead of public, let's make this protected. So by making it protected, we can use it over here inside the unit class. So yep, this works, this is valid code. And importantly, over here on the player, yep, this one is still valid code. We have no errors here. By making it protected, that means that only this class, only the class that defines it, and any classes that extend this base class, any of those can access this protected field. So up here, the player can indeed access the speed, but for example up here in our static, in our main program, over here if we try going into a unit and try accessing the speed field, and nope, it does not work. Unit.speed is inaccessible due to its protection level. So if you make something protected, it is only accessible from within that class and any other classes that extend that class. So if you have some kind of behavior in your base class that the extended classes should be able to modify and only those classes, if so, then make it protected. Or for example, in a field, make it protected virtual. And yep, like this, all the other class can access. So this one just needs to modify into protected override. And then same thing on this one, protected override. And by doing that, the classes that extend that base class, those can indeed access it. But over here, this one can no longer access. Then one really interesting thing is the concept of abstract classes. These are classes that have a definition but cannot be constructed directly. For example, let's say our unit class here, this one should never be created. This should simply be a base class that should be inherited by the player or the enemy or any other kind of unit type, but we're never meant to have just a base unit class. So for that, we can add the abstract keyword. And yep, this one marks this class as abstract. And now if we go up here, yep, we do see this error. Since the class is marked as abstract, we cannot create an instance of this type. This can be really useful to provide a base definition for something, but also make sure that base definition itself can never be used directly. Only the class that extends it can be created. Along with marking a class as abstract, you can also mark functions. So for example, let's make a public abstract and make some kind of void attack function. So we do this and then we just do a semicolon, meaning we do not provide an implementation for this function. And instead, just by defining this, we can see we have some errors over here in the enemy class and the player class. And here, yep, it says that we must implement the attack function. So if the base class has some kind of abstract function, we have to absolutely implement that. And over here, by the way, quick tip, Visual Studio actually has these quick tips. So if you click on this little thing, it tells you to implement the abstract class and it's going to automatically write it. And if there it is, so we need to write that one, and yep, no longer have an error. So this can be useful if you have something where you are not meant to provide any kind of default implementation. You just mark it as abstract and any class that extends this class will be forced to provide their own implementation to this function. But if you do want to provide a default implementation, then just do it like this. Just make a regular virtual function and then any other class can either override or not override. Then another keyword is sealed. What this one does is it prevents classes from extending this one. So as you can see up here we have an error. Since we marked that one as sealed, it is telling us enemy cannot derive from sealed type unit. Now personally, I've never really used sealed, but in complex projects with tons of classes, sometimes it can be wise to make something sealed if it is never supposed to be extended. Again, remember the main clean code principle. The main goal is really to minimize complexity. So if you have some class that is never meant to be extended no matter what, if so, you can make it sealed in order to help you make sure that the compiler enforces that rule. So it can be useful in that way, but personally I rarely ever. So it can be useful in that way, but personally I never really use it. Then yet another more advanced thing related to classes are destructors. So we write those kind of like a constructor. So kind of like up here we have a player constructor. For a destructor, we write it pretty much the same way. So we write just the player as if it were a constructor. So there's no return type, it's just the type. And then before it, we add the tilde key. Which by the way, like it says here, this one cannot be marked as public. So it just runs just like this. So this is a destructor. And now any code that we write here, this is all going to run when this object is destroyed. Which if you remember from what I mentioned in the beginning, C# is a programming language with managed memory. You don't need to directly handle the memory yourself. So the destruction of an object happens when there are no more references to that object. So for example here, let's do a console.writeLine for the player destructor to see when this runs. So for example, over here for some testing code, we're calling some kind of my function, and inside we're just calling a player, so pretty much just constructing a brand new player. And then over here I'm calling gc.collect, so gc stands for the garbage collection. So this is the system that automatically handles all of the memory, and calling collect simply forces it in order to do it. If I didn't force, then this would happen randomly as the program grows. And then just calling another function, just keep it running. So let's see this. And if there it is, just like that. So the player was created, then we call the function. This one created a local variable, meaning that this variable ends as soon as this function ends. So as soon as this function ended, this variable was marked for destruction. Then when we forcefully called the garbage collection, when we did that, it automatically destructed the object and then continued running the program. But remember how destruction of an object happens when there are no more references to that object. So that is why over here, this one is a local variable, meaning it only exists inside of this function. So as soon as we exit this function, naturally this object has no more references to it. However, if instead of describing it in here, let's make a player over here, player test, and then down here, instead of defining some kind of function like that, let's set that field to that. Okay, so just like this, and now if we test, and yep, the destruct does not run because player test, this one is a static reference, and this one continues holding a reference to that object, even though this function has ended. So this is yet another place where it's really important to understand the scope of exactly what code you're writing. One practical example of when to define the destructor is when you have some kind of class that requires some cleanup. Like for example, if on the constructor itself, you open up some kind of file for reading. If you do that, then make sure you close that file on the destructor. So these can be really useful for disposing of any unwanted memory. Alright, so those are some more intermediate topics related to classes. As you can see, there's lots of stuff you can do with them. But also specifically on the topic of inheritance, remember what I said about how it can become really messy really easily, so always use it with care. And something that I mentioned quite a lot in this lecture are interfaces, so let's learn what those are in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn about interfaces. This is one of my favorites and just straight up best features of C#. You define an interface that represents some kind of behavior or type, and then you implement that interface in any class you want. Okay, so interfaces, these are simultaneously really simple and also really powerful. An interface is essentially just a contract. So you define an interface, then you define whatever functions that interface has, then any classes that implement that interface, any of those, they must implement those same functions. So you have a guarantee that anything that implements that interface will implement the functions defined in the interface. By doing this, you can then write code directly against the interface type, and that code will work on any object that implements that interface. This logic is somewhat similar to the class inheritance that we just covered in the previous lecture, except you cannot create an object of the interface type. Another difference is how a class can only inherit from a single base class, but a class can implement multiple interfaces. So for example, with this structure right here, an I-attackable interface that is implemented by both the player and the enemy, with this we could have some kind of bullet object, then the bullet could receive an object of type I-attackable for some kind of target. Then the bullet itself would call the damage function on that I-attackable, meaning the bullet itself would not know if it's attacking an enemy or a player, but because those work with the interface, the bullet would be able to deal damage to both players and enemies. So here's a different demo for some kind of interaction system. I've got 3 objects and I want to interact with all of them. And over here on the building I can click, and yep, I can indeed interact with it. However, clicking on these 2 does nothing. Here is the code running that demo. Now don't worry if you don't understand everything that this is doing, it's not really important. This is just a demo just so we can see the interfaces in action. Over here all we're doing is testing for a mouse click, then we get the mouse wheel position and test if there's any collider under that position, and then try to get the type of that collider. So in this case we're trying to test, are we clicking on something that is a building object, so it has the building component attached to it? If so, then we call the interact function, and that in turn spawns that chat bubble. So this works perfectly fine with the building type, but now let's say I want to interact also with the zombie and also with a push button. Right now it doesn't work. I am clicking on the zombie and the push button, nope, nothing happens. The only one that works is the building itself. That's because over here, this logic, this was made specifically just for the building type, so it does not work with any other type. In order to make this work with those other objects, I pretty much just need to copy paste all of this code, then make this one to make it work with a zombie, and make this one down here to make it work with a push button. Okay, let's see like this. So interact with the building, it works, the push button works, and the zombie also works. Okay, so now I can indeed interact with all the objects, but obviously the code over here does not look very good. We've got tons of duplicated logic. This is really messy code. If we want to add yet another interactable object, we have to come here and copy paste a ton more code. So you can imagine how this becomes really tricky if we have dozens or hundreds of interactable objects. So this is definitely not a good approach. And this is exactly where interfaces come in. Instead of making this code work with each individual type, instead of that, we can make it work against an interface. Here's a super simple interface that I define. Again, I'm going to cover this syntax in a little bit. Then all the other objects, they are implementing this interface. And over here now for the if, instead of testing for each individual type, I'm just testing for the interactable interface type. And if we test this, click on the building and it works, the button works, and the zombie also works. Okay, great. Because we made this code work with the interface itself, That means that this now works with any class that implements that interface. So if I want to make more interactable objects, I really just need to make a new class and implement this interface, and everything won't work. There's no need to touch this code anymore. So this is the practical example. Now let's see the syntax for how we build interfaces. Now the way we define it is really simple. For example, let's define an interface for an object that can be attacked. So we start with the access modifier, and for an interface you probably want it public. Then instead of writing class, instead of that we write the keyword interface, and then we write whatever name we want for the interface. And the general naming rule is to start interfaces with a capital I. This is not required, it's just a good convention to follow. So in this case to represent something that can be attacked, let's call it I attackable. Okay, yep, so this is our interface. Now let's think of what functions we need so that something is attackable, and the answer is we probably just need a damage function. So over here let's type in public, which by the way, everything defined in an interface needs to be public. You cannot define private things inside an interface. That's because interfaces, like I said, they are pretty much defining a contract that other classes must implement. If we were to define something as private, then other classes could not interact with anything inside of this interface. So it wouldn't really make any sense to have any private elements inside an interface. So everything inside of here is public. And by the way, this is actually another reason why I personally really like being as explicit as possible. If you omit the access modifier, if you do that over here on an interface and make some kind of my function, if you do it, then this one will default to public, but if you write this exact same code over here inside a class, if you do it, then now this one will default to private. So this is yet another reason why I like being very explicit. That way there are no questions as to what access modifier we are using for what element. So over here I like to be very explicit and write public void, and let's call it damage. And yep, we just define the function and then put a semicolon, meaning we do not write an implementation in this interface. Here we are just defining the function signature. So that's just the name, the return type, and any parameters if there are any. And that's really it. We don't provide any implementation. In our classes, like for example, let's make a random player class. And now on this one, we can implement our interface. And we do that pretty much exactly how we saw for extending a base class in the previous lecture. So we add a colon and then our interface, so I attackable. And if there it is, just like this, and we have an error, and if we see, yep, the error because the player does not implement the interface member iAttackable.damage. Again, like I said, if you implement an interface, you have to implement everything within that interface. So over here, you absolutely must implement this damage function. And since the interface itself, since this one has no function body, because that we can have whatever implementation we want, meaning the player can have some kind of implementation, then the enemy can have a different one, and so on. So pretty much similar to what we saw in the previous lecture on extending base classes, how we could override and provide different implementations for the same function. Over here, it's kind of a similar thing. So let's do a public void damage, and here we can, let's just do a console.writeLine and just print out player damage. Okay, so yep, that's it. And now, for example, up here in our main, let's make a field of type iAttackable. And now we can simply construct a player and we can assign it over here. Yep, just like this works. Again, similar to what we covered in the previous lecture. This is polymorphism in action. Since the player implements the iAttackable interface, we can use a player object and assign it to a variable of type iAttackable. And then through this interface field, through this one, we can access whatever functions we have in our interface, like for example, damage, and yep, this does work. So now we have similar benefits to what we saw in the previous lecture on inheritance. For example, let's make another class. Let's make an enemy class that also implements iAttackable. And yep, just like this, it works. And now up here, if we have some kind of code that works against the iAttackable interface, like for example, let's make a private static void attack object, and we receive an object of type iAttackable. So we can do this, and then on attackable, we can call damage. And now up here, we can call this attack object, and we can pass in an object of type player, and pass in one of type enemy. And yep, both these work just fine. So this function over here that was written directly to work with this interface type, it does not care what object we pass in as long as that type also implements our interface. Now, one limitation of interfaces is they cannot have fields. So for example, down here in the interface, let's make a public int health. And nope, this does not work. Interfaces cannot contain instance fields. Again, this goes back to the difference between an interface and a base class. A base class can contain actual data, since a base class can be constructed. But an interface, this one is just a contract, so this one holds no data. So that is why over here we cannot have any fields, but we can have properties. So yep, this does work, so we can define a public health property. And again, same thing, all of these need to implement that one. Then we can also have functions, of course. Then we can also have events, which we're going to cover later. So the main limitation is really how you cannot have fields, because again, interface cannot store any actual data. Another thing is actually here we define this function with no body, and then the classes must implement that function. And this actually used to be the only way, but in recent C# versions, you can now add an optional default implementation. So you can write a function here and just write the code as normal. So you can do this, and now classes that implement this interface, they are not absolutely required to implement this damage function. If they don't, then it's simply going to use the default one. So as we can see over here, we have no error. And up here, we can still pass in an enemy, and through this function, we can call damage function. And the only thing is one is going to run the player damage, and this one is going to run default. So let's test. And it picks out like that. So the player did implement their own custom implementation, but the enemy didn't, so it used the default one. This feature for default implementations, this is especially great when working with some complex projects, things that are already using a bunch of interface and you want to add a bunch more behavior. If over here you just add a brand new function, so test function, if you just do this, then all of a sudden we broke all of this code. This is obviously not very good. So if you do this, if you add after the fact and you don't want to break your current code, just provide default implementation and yep, now everything does work. So like I said, interfaces look slightly similar to class inheritance. However, one huge difference between them is how you can only ever inherit from a single base class, but you can implement as many interfaces as you want. So for example, here we can make an interface and let's call it iMovable. So this would represent something that can move. Then an interface, call it I has inventory. So this represents something that has an inventory. Then up here, let's say the enemy can move but has no inventory, and the player can move and has an inventory. And yep, we can implement all of these interfaces. In the previous lecture, I talked about how you should prefer composition over inheritance, and this is exactly one way you can do that. You can have interfaces that each define some kind of behavior, like for example, whether the object can be attacked, whether it moves, whether it has an inventory. You can do that, and then your classes, you can implement only the interfaces that are related to that object. So for example, the player can attack, can move, and has an inventory, but the enemy does not have an inventory, so does not implement that interface. This is a much better pattern as opposed to making all of these requirements on some kind of unit base class, and then the enemy would also have some kind of inventory even though they would never use it. So this is an example of composition over inheritance. And for example, in my game Thinking Guardians, I use interfaces all over the place. I use them to define all kinds of behavior and then have tons of code that works directly with those interfaces and really does not care what the underlying type is implementing that interface. So it can be a dinky, it can be a machine, it can be the player, it really does not matter. As long as that type implements that interface, it does work. One extremely common interface in games is simply making some kind of interaction system. So just like we covered in the demo, and if you want to learn more about specifically that type so you can see a practical use case, if you want you can check out my dedicated tutorial on how to make an interaction system, do something that can talk to NPCs, push buttons or open doors. And like we saw in the demo, if you don't use an interface then you have to copy paste a bunch of code, but if you do use an interface then it makes it super simple for your system to work with any object you want. So interfaces are really truly awesome. They are definitely one of my favorite C# features. They are extremely useful, so definitely make sure you fully understand them. They will help you a ton in pretty much any game, any code you want to make. Now that we've covered interface and inheritance, these are two things that deal with a lot of types that work as different types. Now that we've done that, we're ready to handle the various ways of doing type conversion, so let's do that in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn some things about comparing various types. We're going to see whether they're an interface or a base class, and we're going to see how we can convert between them. Okay, so previously we already covered inheritance and interfaces. Those are two ways we have of handling an object of a certain type that also works as a different type. For example, if we have our iAttackable interface, and both the enemy and the player implements that interface, if we have a field of type iAttackable, over here we can construct a new player, and yep, it works. And we can construct a new enemy, and yep, this also does work. But then let's say we have some special logic that we only want to run if the object is a player and not an enemy. For example, over here on the player, let's define a public void, player say hello, something like this. So if we have this function that only exists on the player, so it does not exist on the enemy, on the unit, on the interface, nope, only exists on the player. And over here, if we have a field of iAttackable, even though we placed a player object inside that field, if we go through it and try to call player say hello, nope, this does not work. Like it says here, iAttackable does not contain a definition for that. So it does not really matter what is the specific object that we have stored inside this variable. This variable is of this type, so we can only interact with things that exist inside of this type. If you have a field like this and you want to see if the underlying object stored in there is of a certain type or a different one, if so, you can do if attackable and then use the keyword is, and then the type is player. So we can say this, and let's do a console.writeLine just to see if this one is a player. Let's just get rid of this code for now. Okay, let's see if this one prints. And if this print, that object is indeed of type player. And if we replace this for an enemy and run, and if that one does not print because this one is no longer of type player. So this is the simplest way for how you can tell if a certain variable, if the object stored within that variable is of a certain specific type. Alternatively, on pretty much every other object, we can see we have a bunch of functions that are available to every single object, like we already saw the toString, so this one exists on every object. But the other one that is also super useful is this one, the getType. This one returns the specific type of that object. So for example, let's do a right line on this one to see what this one says. Okay, so let's print this and see what this one says. And if that one says the type, so this one is of type enemy. So here we can get an object of type, which actually tells us the type of the object that this is. So over here we can check the attackable.getType in order to get the type contained within that variable. And instead of using is, we simply compare with the type of player, except like this we have an error. Because player, this is the name of the class. In order to get the type, we use the keyword type of. And this returns the type of whatever is within the parentheses, so in this case the player type. And yep, this now works the same thing as we saw previously with the is. So this one, this is an enemy, so this is not going to run. And if there you go, it's an enemy. But if we swap this for type player, and if there it is, now it does run. Now, one difference between this getType method and the other one using the is keyword, one difference is this one does not check for inheritance or interfaces. So if we see is of type iAttackable, which again, the player class, this one is indeed implementing iAttackable. So let's see if this one runs or not. And nope, this one does not run. So if you use this method of getting the type and using a type of to do an equality check, if so, when it comes to interface, instead of that, you can access the function inside of this. Specifically, the function is interface. This will tell you if this type is an interface, and then you have a bunch more. You have a function for checking if it's an instance of a type. You can check if it's a subclass of something, or you can check if it's assignable to and from something. Or alternatively, for this case, for testing against interface, you can use the previous method, which personally is the one that I prefer. So just do if the attackable is iAttackable, which in this case doesn't make much sense, but let's test. And yep, it does work. But if we were to make a new player over here, let's see. And yep, it does work. Alternatively, we could test if the player is a unit. And yep, this also works. So there are various ways to test if a certain variable, if a certain object is of a specific object type. So for example, let's go back to our original demo. So testing if the attackable is a player. And if so, we want to run this specific function on the player class. Right now, even though we have identified that this object is of type player, we still cannot go here and call player say hello. Nope, this still does not work. Even though we have verified that it is of this type, we still need to convert it onto that type. And for this, we also have two options. One is using the as keyword, so let's define a player field. And for this, let's use the attackable as of type player. So if we do this and now do this, and over here, let's just print out something. Okay, let's see. And yep, it does work. It did run that. So here we convert our attackable into a specific player type, and then we can call any functions that are specific to this player type. The other conversion method similar to this one is simply casting, which we already saw when we cast some floats down into ints. So instead of using attackable as player, we just put player in parentheses and then attackable, and like this. And yep, it does work. So these are two ways for converting types, and the difference is usually related to whether the conversion succeeds or not. So for example, let's go outside of the if testing the player. Let's just comment this out. So up here, let's create a new player, and then let's create a new enemy. And now let's do a player test player, and we're going to take the enemy and cast it down into a player, which obviously this will not work. It does not work because enemy has no relation to the player itself. The enemy implements the attackable, extends a unit, but has no relation directly to the player itself. And in this case, the compiler doesn't even let us run this code. However, we can try forcing something that won't work, so let's put it in iAttackable, and up here on this attackable, let's make it of new enemy. So this one is an enemy, meaning this one will not work, but now we don't have a compiler error because technically iAttackable might be convertible into a player. It might or might not be. And if we test this, and yep, if we try to cast something that does not work, we're going to have this error, unable to cast of type enemy into player. And using the other method, so let's see what that one does. So attackable as player. And in this conversion method, we have no error. And let's just do a console.writeLine to see what is stored on that one. Let's see. And yep, it's empty, meaning that one contains null. So this is the difference between the two methods. If you use a cast and the cast fails, it is going to throw an exception. Whereas the as, if the as fail, it is simply going to store null over here on this field. So remember this difference. If you use this method in order to figure out whether this cast worked, if so, then compare this one against null. Or if you use this method, then before you do, make sure to test if the player is actually castable. Which up here, this code is normally what I do. So I just check if something is a specific type, and only if so, that's when I cast down and then do some complicated logic. Also related to type conversion, when working with value types, like for example an int, on this one, if you do some kind of thing like this, so a as float, if you do it, nope, it does not work. The as operator must be used with a reference type. That is because, like we saw, if this one fails, this one is going to return null, but a value type can never be null, so that is why the as keyword can only be used with reference types. So when you ever have this kind of thing, you only have to use the cast option. And something related that I mentioned briefly in the beginning of this course is how every type in C# is convertible down into the object type. This is the base type for pretty much anything in C#. You can convert any type into an object. So for example, something you can do is define some kind of int, then you define some kind of object, and you can place an int inside of that object, and then you can define another int, go inside the object, and cast it down back into an int. And yep, this does work. This is technically something that is called boxing, which I'm going to cover in more detail in a lecture in the advanced section. This is basically how you can convert anything onto an object and then convert it back. This topic of type conversion is also something that will be very important in a few lectures when we cover events. The default type for any kind of event is the event handler. And this one, if we inspect how it is, yep, this one has a parameter of type object. So when working with this, we're going to need to do some conversion. And usually for events, you know what type is firing this event, so you can just use a cast in order to convert this object onto whatever type you want. But like I said, I'm going to cover events in a few lectures. So with that, here we'll learn the various ways of handling type conversion. These can be very useful when combined with interface or inheritance. Anytime you need to do some kind of type checking or convert back and forth between one or two types, now you know the various methods for doing it. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn about switch pattern matching. This is how you can do a switch on a type instead of just a value. This is a super quick lecture since it's actually really simple, but I wanted to make sure you definitely know about this. Okay, so we already learned how to handle multiple types with inheritance and interfaces. Now let's see a more advanced use case for the switch that is perfect for this scenario. So in the last lecture, we already covered how to check if an object is of a certain type. So for example, if I have an iAttackable field and I set this to a new player, then we can check if attackable is of type player, and if so, do some kind of logic. Then we could also test if attackable is of type enemy. We could check if it's of type of the red barrel. So yep, this works perfectly fine. But just like we saw on the lecture on the regular ifs, if you have to do a ton of them together, then at that point a switch is better. And actually on a switch, we can also do this kind of logic, testing if a certain field is of a certain type. So instead of this, let's do a switch and switch on attackable. And then on the case, we can add the type definition. So for example, case player, and then assign it to some kind of variable name, player. And if there it is, this is valid code. What this is going to do is, if the attackable is of type player, then it's going to cast attackable onto a player type, and it's going to assign that reference over here on the player. So for example, over here, we can access the player and call a function that only exists on the player, like this one, player say hello, so this one. And yep, this should work, so let's run. And yep, exactly, it does work. So here, this is both testing a specific type, it is also casting that type and assigning a variable reference. So with this, instead of having all those ifs, we can do here case enemy, enemy, and case red barrel, red barrel. And yep, all of these now work. So now inside of this, we can put any kind of enemy-specific logic. And of course, we always have the default case, just in case it does not match anything, then it's going to run this code. Also, this actually lets you do one more thing that I actually didn't know until I did the research for this course, which is on this case, you can add extra conditions. So for example, up here on the player, let's define a int for the player health, something like this. And now up here on the player, we can use the keyword when, and then define some kind of condition. So for example, when player.health is above 50. If so, then we're going to run this and put one without it, and it's going to run this. So over here for test, let's do a console.writeLine on this. So this one health 50 and the other one is the default. Now up here on the player, let's construct it and let's put the health on 100. So that should go inside of this one. So let's see. And if exactly goes inside that one, whereas if over here, if the health is 20, and if there it is, it only runs the other one. So this whole thing is called switch pattern matching. So as you can see, we can do a switch and then define all kinds of patterns. And depending on which pattern it matches, it's going to run different kinds of code. With this, the switch can be used in tons of ways. So not just testing for a specific value. You can cast into a type and then couple it with some kind of condition. And doing that, you can do all kinds of logic on different switches. But again, always remember the #1 rule. Code is meant to be readable and understandable. So if you end up with a mountain of switches with tons of complex when case conditions, at that point, it's probably best to refactor your code in some way. But for simple use cases, this is really useful, especially for this kind of use case where we have some kind of base class or some kind of interface, and we want to do some specific logic depending on what type it is. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn about delegates, lambdas, and anonymous functions. Okay, so delegates, they are a really powerful C# feature. They basically let you store a function inside a variable or use it as some kind of parameter. Here is a working demo. So I can click and it spawns a chat bubble. Then I can press a button to change the action. And now if I click, yep, now it spawns a regular sprite. And now press another button. Now I click and yep, now it's spawning some particles. So the same action, clicking, is doing different behavior based on what action I select. Here is the code for the click actions. And the delegate is this one over here. It's something of type action. This is a delegate. And then I've got a bunch of functions defined here, so spawn chat bubble, a sprite, or a particle effect. And I can see over here on start that I'm assigning the click action to this function. So importantly, it is not calling the function. Nope, it is passing in the function itself and storing it over here inside of this field. And then on mouse click, I simply run whatever is stored inside that variable. So the variable stores a function, and then by calling this, I can run whatever function is stored within that variable. Then these buttons simply do that. They simply assign a different function onto that variable. And with that, I can click, do one behavior, press to select something else, do another behavior, and another one just like that. So this is a practical example. Now let's see the syntax. To define a delegate, first let's write the access modifier. Let's go ahead with private, and then let's use the keyword delegate. And then you write essentially a function signature. So let's make something super simple. For the return type, let's use void. Then for the name for this delegate, let's call it attack delegate. Then we add any parameters we want, or basically none of them. Okay, so yep, so just like this, we have defined our delegate type. Now we can use this type just like we can use any other type. So for example here, let's make a field of this type. So let's make it of type attack delegate. And let's give it some name like attack action. Okay, so just like this. And then, like I said, the goal is you can store functions inside a delegate variable. So over here, let's make a regular function. Let's call it melee attack. And let's just do a console.writeLine. And let's print out melee attack. Yep, just like this. Now, importantly, we need to make sure that this function signature has to match our delegate signature. So it needs to match a return type, so both need to return void, and needs to match a number of parameters, so in this case 0. So with this, yep, now we can go inside our attack action, and we can assign it to our melee attack. And again, importantly, we assign it just like this, so we assign the function itself. We do not call the function. No, this is very different. We assign the function itself just like this. So you can do this, and then basically we can run whatever function is stored within this delegate. And we do that by calling it like we call any other function, so just like this. Okay, let's test. And if exactly it ran our melee attack function. So for example, you could have multiple enemy types, each with different attacks. In order to trigger those different attacks, you would simply assign a different function onto the delegate variable. Then, like I said, the delegate can have whatever return type and whatever parameters you want. So for example, let's make another delegate. Let's make one that returns int, call it my delegate, and let's receive a string parameter. So just like this is the delegate reference. And like I said, when assigning something of this type, so for example, down here, let's make a field of this type, my delegate. And now when assigning it, like I said, it needs to match the function signature. So if I try assigning melee attack, and nope, we have an error. It is telling us that there is no version of the melee attack function that matches the delegate my delegate. So there's no version of this function that returns an int and takes in a string. So in order for this to work, let's go make a private static void my test function, and actually not void, so actually in here let's return an int and let's receive a string parameter. So we have this one, and now up here we assign this to this field of type my delegate, and yep, now it does work. Let's just return 0 just to fix that error. And yep, like this does work. It works because the function signature now matches, so they both return an int type and they both have a string parameter. Also, by the way, over here you need to define some kind of name for the parameter. So like this, it's an error, so you need to define it with some kind of name. But down here, when you assign the proper function, this one does not have to have the exact same name. It needs to be the exact same type, but not the exact same name. Okay, great. So this is the basics of delegates. So up here, we define a delegate and then we assign it. So that's great. And delegates are really super useful. I use them all the time, but always having to define them before you use them, that is a little bit of a pain. So for that, C# has some really awesome default delegates that are super useful. One of them is simply called action. So let's make a field and let's make it of type action, which by the way exists inside the system namespace. So action, let's call it my action. And we can inspect the action in order to see the function signature for this delegate. And yep, this is a delegate that returns void and takes in no parameters. So pretty much exactly the same that we defined up here. So down here, if we grab my action and we assign it to the melee attack, and yep, this does work because again, the function signature matches. This one returns void and has no parameters. So rather than having to constantly define your own custom delegate with void no parameters, if you want that, you can just use action. And then there are actually various action definitions. you can add the angled brackets. This means a generic. We're going to cover what are generics in detail in a future lecture. So on this you can see there are 16 versions of this type, and these are basically just different amounts of parameters. So you can see there's all the way up to 16 parameters. Basically on these you can include whatever type you want for the parameters. So let's say an action that takes in an int. What this means is a function that will return voids, and it's going to have an int for the parameter. So the equivalent, for example, up here would be some kind of int like this. So this would equal pretty much this. And down here, of course, since we changed the delegate that we're using, this one is no longer valid. So in this case, we would need to make something that returns void and then takes in an int parameter. Yep, just like this. And if we assign this one to that one, and yep, it does match. So action is really awesome. It's a built-in type, so rather than having to define your delegates, you can just use this directly. The only thing is that action always returns void. So all the various versions that we saw, all these 16 versions, every single one of these is just affect the number of parameters, but they always return void, meaning they cannot return any value. If you do want a delegate that returns something, for that you have the func, and this one works pretty much the same as the action. So this one also has tons of things. So let's put in the generic in order to see all the types. And this one, as you can see, has a generic named tResult. So this is basically going to be the return type, and then has all kinds of those for all kinds of parameters. So this is basically going to return some type and then have any number of parameters. So for example, in this case, this my func, this one is of type int, meaning it's going to return an int. So let's actually define it. So let's take this one, go down here, and we're going to need to assign it to something. So let's make another function that matches that delegate. So again, this one has no parameters and it's going to return an int. So let's make it return an int and with 0 parameters. And if we take this and let's just return 0. And if we take this and assign it, and yep, it does work. So the built-in action and func delegates, these are super useful. If you have some common use case, you can really just use these two. There's no need to define your own delegates, but defining your own delegate is also still something proper. The one big benefit is, of course, this one has a custom name. So even though this one perfectly matches an action delegate, with the name attack delegate, that makes it a bit more clear as to what the intent is, as opposed to this one func. This one has no clear intent on what it's doing. So they both have their use case, but in many ways, for simplicity, when you just need something basic that works, using func and action, those are excellent. Then for assigning a delegate, so over here we are creating something of some type, then we are creating a separate function and then assigning it. So this works. But we can also do what is called an anonymous function, or sometimes called a lambda expression. So for example, let's define a field of type action. And now when assigning it, we can just put in the parentheses for the parameters, which in this case action has no parameters. And then we do a little arrow symbol, and then let's open and close a code block. So yep, just like this. This is valid code. What we have here is a lambda expression for defining some kind of function that takes in no parameters and returns nothing. So what we have here is pretty much the same shorthand as what we have here. We can place the console write line there, and yep, this is exactly the same as this. Except when doing this, we didn't have to define a completely separate function. So these lambdas, this is another really super useful thing. I use them all the time, especially when writing any code for buttons. In Unity, buttons have a click action, and normally I just use a lambda in order to define what behavior I want when I click on a button, as opposed to having to write a separate function and then assigning it to the delegate. So lambdas are really great time savers, and you can use them on any delegate type. So over here, an action with no parameters, but if we make an action that takes an int parameter, if so, then you just need to define the int parameter over there. And if this does work, and alternatively, if we make a func, let's make a func that takes an int and returns a bool. So this one takes an int parameter, and then over here just needs to return some kind of boolean. Yep, that works. And then alternatively, if you want, you can even simplify this even further. So let's erase all this. Let's put just false, just like this. And yep, this is perfectly valid code. This is doing the exact same that we saw previously. The compiler is smart enough to know that if this delegate expects a return value, it is smart enough in order to add the return into whatever statement we write. So this is perfectly valid code, although normally, like I said, I prefer being explicit. So personally, I prefer to always write everything perfectly. Now, one interesting property about delegates is multicast, meaning how you can store multiple functions inside a delegate. So for example, let's see here our attack action. So we're assigning it to just the melee attack. Let's make another one. Let's make a range attack. And over here, if we do this and then assign it to the range attack, if we do this, and let's just get rid of the other code. So if we run this code, and if there we go, it only runs the range attack. However, instead of assigning, we can do plus equals. And now if we run this, and if there we go, now it ran both. Even though over here on the delegate, we only ran the delegate once, since the delegate itself is storing the reference to two separate functions, it is going to run both those functions whenever we run our delegate. So this means that the delegate itself, it can store multiple objects, it kind of has a list in the background of all of the functions that are stored within it. And since you can do plus equals to add it, you can also do minus equals. So let's run that one, which should run both, then do a minus equals and then print, and let's see this. And if there you go, so the first time that we ran the delegate, the first time it ran melee attack and range attack, but the second time, since we raised the range attack, we did minus equals, because that the second time it only ran the melee attack. Now, one really common use case for delegates is doing asynchronous programming and handling callbacks. If you're familiar with JavaScript, you're certainly very familiar with this. And in game development, for example, one very common use case is for pathfinding. You tell a unit to move somewhere, and you can pass in a delegate for what to do when the unit gets there. So for example, here's a basic unit class, and it has some kind of pathfinding, so it has some kind of move to function. It takes in a target position, then an action for the onReach target action. So we would create a unit, we would tell it to move somewhere, and we would pass in a delegate. So in this case, it could be a simple lambda, so a simple anonymous function. We could pass that in, then the unit would do all kind of movement, and eventually it would reach the target, and when it reaches the target, then it would call that function. And in doing so, then it would run whatever logic we set when we call the move to function. So if we test this, yep, there it is, now the unit is moving, and after a while it gets there, and yep, it reaches the target. Another common use case is when doing something that contacts a web server, so some kind of web request. I made a tutorial on that, and for that, I made the class receive a delegate for the callback that is called whenever the server responds. So delegates are super useful, extremely versatile. It can be sometimes a little bit tricky to understand at first, since they look like variables, but they're actually storing functions. If there's something you didn't understand, definitely go ahead and rewatch this lecture once again and go through the interactive exercises. This is an extremely powerful feature that you absolutely must understand. Now here I mentioned lambdas for making anonymous functions, but there's actually another way of doing something similar. We can create normal local functions, so let's learn the differences between them in the next lecture. Hello and welcome, I'm your Code Monkey. In this lecture we're going to learn about local functions and how they differ from lambdas. Okay, so in the previous lecture we covered delegates and lambdas. Lambdas are one way to make an anonymous function. So if we have some kind of action, my action, we do a lambda by writing the parentheses with the parameters, then we do a little arrow and a code block just like this. This is a lambda expression. However, there is another method for making anonymous functions. It's called local functions, and they're exactly like the name implies. Just like you can have local variables, so in something, so this is a local variable. Just like this, you can also define a function within another function. And you define them pretty much exactly the same as another function. So for example, void print, let's receive a string message, and then we put a code block, and inside, let's go console and write line, and let's print out the message. And if that's it, here we have a valid local function. We have this function inside this main function. Now, naturally, we cannot call this from anywhere else. So if there's another one, so another private static void. So if we have another function here, from this one, if we try accessing print, nope, this does not exist. So this is a local function, which just like a local variable, is only accessible within this function. And we saw the delegates in the previous lecture, so we can use these exactly the same way. So action, my action 2, and I can assign it to print. And actually this one takes a message, so let's do action of type string, and yep, there you go, this is perfectly valid code. So here this, and here this, just put a string here, just to make it exactly the same. So a string message like this, and yep, both this and this are exactly the same thing. Now let's see the differences, and first is really just the syntax. You can see how the lambda over here, this one does not have a name by default. The only way to reference this lambda expression, the only way is by going through the actual delegate that stores it, whereas the local function over here, this one has a proper name. You don't need to assign this to any kind of delegate field in order to be able to actually use it. Then another thing is how the local function can be defined anywhere. So for example, I can define the print in there, and up here I can call print. And yep, this is valid code. There's no errors. Again, only inside the actual function code block because it's a local function, but I can define it down here and use it up here. This is valid. Whereas with the lambda, you cannot do this. If I try accessing the my action, nope, obviously there's an error. I cannot use a local variable before it is declared. Whereas for the local function, that one works just fine. The difference for this is because local functions, these one are defined in compile time, whereas lambdas, these are defined at runtime. So because of that, the compiler knows that this function is coming, so it can use it, but this one can only be used after it is declared. Also importantly is how the delegate over here, the lambda, this anonymous expression, lambdas are actual objects that are declared and assigned at runtime. They are actual objects that exist in memory. So every time we run this my action, every time we do that, it is going to create a brand new object. Every time we run the main function, every time we do it, it is going to create a brand new instance of this object. It's going to create a brand new lambda. Whereas local functions, these are defined as compile time, so in memory they only exist once. So we could call the main function 100 times, and it would create 100 instances of this lambda, but only one instance of this print function. So in terms of memory, if you're memory limited, then local functions would be a better option than using lambdas. So in general, both local functions and lambdas serve a somewhat similar purpose. They allow you to define functions whilst inside another function. Local functions can be great for organizing logic within a function, assuming whatever you're doing in that function is only ever done within that other function. And lambdas are great for super quick things like assigning logic to a button click. For the most part, personally I really only use lambdas, but local functions also have their use case. Hello and welcome, I'm your Code Monkey. In this lecture we're going to learn all about events. This is another extremely powerful feature of C#. It helps us write much better code with much fewer dependencies. Okay, so events. This is basically how you can have one class, and that class fires off events when something happens, and the subscribers that listen to that event, those will be notified whenever that event happens. For example, here's a working demo. So there's a tower and I can click to damage it, and by using events we can have some kind of health bar, and that health bar is listening to when the tower takes damage, and when it does, the health bar listens to that event and updates its own state. So the UI element over here, this one is listening to the build damage event itself and then updates the health bar. Events have publishers and subscribers, or sometimes subscribers are called listeners. Those two terms are really used interchangeably. The event is defined within some kind of class, and then you can listen or subscribe to that event from anywhere else. Now what that means is that when the event is invoked, all of the subscribers, those all get notified that the event happened. And note how this relationship only goes one way. So the subscribers attach to the event in order to be notified, but the event publisher, this one has no idea that there are any subscribers. This is really excellent for keeping your code decoupled. The event publisher does not know and does not need to know if there are any subscribers at all. Maybe there are some, maybe there are none, it does not matter. The event publisher itself is completely decoupled from any subscribers. As far as the event publisher knows, it just knows that it fired off an event. That's it. It does not know and does not care if anyone is listening. And the other benefit of using events is that our code can be based on when things happen as opposed to constantly polling for something. For example, over here on this demo, the health bar does not have to constantly poll the tower to check its health state on every single update, so it does not have to ask that question 60 times a second. The health bar is perfectly idle. It only listens when the event is published, so only when something actually happens does the health bar take action. Here in the code, the tower script, this one has an on-damage event. Then this demo is really super simple. I'm just testing for the mouse click, and if so, calling the damage function, and damage function simply alters the health amount and fires off the event. Again, note how this tower does not know anything about any kind of health bar. It is completely decoupled. And then on the health bar itself, this one does know that tower exists. It attaches itself to the on-tower on-damaged event. And when that event happens, it simply updates the health bar. So in order to show how the code is decoupled, I can just go ahead and get rid of the health bar. So I can just disable this game object, and yep, everything does work, because the tower does not depend on the health bar. Okay, so that's a quick overview of events. Now let's see the syntax. And the way that we make events is actually super simple. This lecture will be really easy to understand because we already learned about delegates, which are quite closely related to events. First, we write our access modifier. And usually for events, you do want them to be public. You want it public so that any other classes can listen to that event. It doesn't make much sense to have one event that is only listenable from that class, so usually events are public. And then we add the keyword event, all lowercase. This is a special keyword. Then we add the delegate. And like we covered in the delegates lecture, we can define our own custom delegate, or we can use the built-in action, for example. So let's use this one just because it's so easy. And then we give it some kind of name. Usually the convention is to start your event names with on, and then whatever happened. So for example, on player damaged. Simple like this, and in terms of naming rules, events are usually Pascal case, just like properties. Okay, so great, so just like this, we have defined our event. Now let's write a quick demo, just see how it works. And for that, let me actually just put this inside a basic player class, just so the demo makes a little bit more sense, so put it inside there. And now let's make some kind of damage function, so let's call it damage. And now here, the first thing we can do with our event is simply fire it. And for that, we do it pretty much as if this was a normal delegate and we were just calling it. So let's go on player damage and simply call it like this. So that's it, super simple. However, this code will actually throw an error, but let's test it like this. Up here, let's just create a new player. Just construct a brand new player, then on player, let's call damage and let's test. And if right away we have an error, we have a null reference exception. So this has to do with the fact that this event currently does not have any listeners. If it has no listeners, then this field is essentially set to null. So before invoking an event, we need to check if it has some listeners. And we can do that just by checking against null. So if the event is not null, if so, then that means it has some listeners, so we can safely call that event. So like this, if we run, and you have no errors, although also nothing happened. So now that we are correctly firing off the event, let's add in listener. Let's make another class. Let's make it a class and call it player health bar, something like this. And now in order to listen to the event, we need some kind of reference. So let's actually make a constructor for our player health bar. And in the constructor, let's receive an object of type player. So we receive that, and now here we can go through the player. And now we can indeed access the on-player damage event. Also here in Visual Studio, it shows this little lightning bolt. This means an event. So we can access that event, and then we can do plus equals in order to subscribe to that event. And here, by the way, Visual Studio has this really nice shortcut. It is going to auto-write the player on-player damage event. So just press tab to insert. Usually I do this. Then if you want, you can rename it or just press enter, and yep, there's our event function. Now, if you don't see this shortcut, or if you're using a different ID, you can just manually write this function. It's a pretty basic function. The only important thing is, just like we covered in the delegates lecture, the function signature needs to match event signature. So in this case, for the event, we made it of type action, which means it must return void and must have no parameters. Okay, so here we are listening to the event. Let's just do a log, so console.writeLine. Let's just print out the on-player damage event, just like this. And now up here, let's construct our player health bar. So let's construct a brand new one. Let's make it. And this one requires a reference to our player, so let's pass it in. So first we create the health bar, and then we call damage on the player. So now basically what will happen is when we call damage, the player damage, this one is going to fire the on-player damage event. It is going to check against null, and since we have a listener, this one is not going to be null, so it is going to run our event. And by running that event, it is essentially going to run this code and print this line. So let's see. And if there it is, the event was fired and the listener did listen to that event. All right, awesome. Again, note one of the big benefits about events. The player class, this one has absolutely no relation to the player health bar. So the player class is completely decoupled from the player health bar. As opposed to, for example, if we were to make this public, and then up here we would have some kind of private field of player health bar, then we would need to keep this reference, and in doing this on the damage, we would call the player on damage function. If we did this, then the player class would be tightly coupled to this one. So for example, if I remove this one, obviously there are errors because this type no longer exists. Whereas if we go back to what we had previously, here is just the event, here is just the player class, and if I completely remove this one, yep, there are no errors inside the player class. This is what it means to be completely decoupled, is that the player class does not know and does not care if anything listens to that event. If it does, then great. If not, then also great. Then one important thing about events is how multiple classes can listen to one event. For example, if over here I make another one, let's make this a mana bar. So do it like this, do it pretty much the same, and over here let's say mana bar something. And then up here, if we construct a new of type this, if we do it, then now we have two listeners to this event. So when this fires, it is actually going to run both of these listeners. And if there it is, both of them did run. So events can be listened to by multiple listeners. And then over here, we are subscribing. But if you want at some point to stop listening to that event, you can simply swap the plus equals to minus equals. And yep, with that, we can unsubscribe. And at this point, I should point out that unsubscribing to events is actually very important. If you don't, then you might end up with memory leaks, depending on the lifetime of the object. If the listener gets destroyed, but the publisher lives on, if so, then it will actually keep firing events onto a listener that no longer exists, so that could cause all kinds of issues. So always keep that in mind. Either pay attention to the lifetime of the objects, because if the player has the same lifetime as this one, then technically you don't need to unsubscribe. But if they do have different lifetimes, if so, then when this object gets destroyed, make sure you unsubscribe to that event. So yep, we can either do plus equals or minus equals to subscribe or unsubscribe. And on the class that defines the event, we can also call the event. And now right away, you might be thinking that this looks exactly like delegates, especially the delegate multicast function. And yep, that's right, this is indeed very similar to delegates. In fact, if over here I just remove the event keyword, if I do, nope, nothing changed, there are no errors. And if we run this, yep, everything still ran exactly the same. So technically it works like this. However, adding the event keyword had some really useful limitations. First of all is who can trigger that event. If we do not add the event keyword, then anyone with access to this event can invoke it. So for example, down here on the player health bar, I can go on there, call it, and yep, this will work. So this player health bar will be invoking this event. Usually you do not want this. You want the class that defines the event to be the only one that can actually invoke the event. And if you add the event keyword, then the compiler actually enforces that rule. So yep, down here, nope, it cannot call it. The event can only appear on the left-hand side of a plus equals or minus equals, so subscribing or unsubscribing, except of course when used from within the player class, within where the event was defined. So the event keyword is really nice for essentially protecting you for yourself. Remember how the main clean code principle is simply minimizing complexity. So the more you minimize access to a particular field, the better it is. Another limitation that this keyword adds is simply the ability to clear the event. So again, if we remove it, then for example, down here, the player mana bar, this one can go into the event and set it to null. And if we test the code like this, Yep, look, that issue. Basically, the meta bar completely erased the original event listener. So the player health bar, this one no longer listens to anything because this one pretty much broke the code. Again, this is something you don't want to happen with events. And again, this is something that just by adding the event keyword, the compiler will help you by enforcing some rules. And yep, like it says here, once again, same thing. By adding the event keyword, the only thing you can do outside of that main class, the only thing you can do is subscribe and unsubscribe and nothing else. So in many ways, events are indeed pretty much delegates, since they in fact actually they use delegates. Like we saw here, we are using the action delegate. But the event keyword, that one adds some really nice limitations to basically protect the code from yourself. And of course, since he used delegates, we can use anything more than just a simple action. If we want to pass in some data for the event, we can really just use a delegate with parameters. So for example, let's use an action of type int. And then over here, when we call the event, we can pass in any kind of int value. And then down here on these, in order to listen, again, the listener function needs to perfectly match that one. So if this one expects an int, then over here, we also need to put an int. And yep, like this, it will also work. And the parameter over here will be whatever you do when you call the event. Now, another thing is over here, we've been using the action delegate. You can use whatever delegate you want. You can build your own delegates, or you can use action, the built-in type. But in general, the C# standard is to use the event handler. This one right here that exists inside of system. This one has a signature where it takes in an object for the sender and an event args. So usually when invoking the event, for the object sender, you pass in this. So you can pass in a reference to whatever object was firing that event. And for the event args, if there aren't any, you can just use the constant event args.empty. So yep, just like this. But again, this is not a requirement. Like we saw, you can use pretty much any delegate you want. You can use action and everything works just fine. But generally, this is the C# standard. If you see a bunch of C# code, chances are they're going to be using the event handler. And then this one actually has a second parameter that defines what are the event args. Again, that parameter is also used with generics, so let's open up that one. And yep, it has a type of event args. So while following the standard, if you still want to pass extra data, you can. For that, usually you make some kind of class that extends event args. So here, let's make a class. And usually the standard name is to give it the same name as the event, so on player damaged. And then you simply append event args at the end. And we make this a class that extends event args. Simple like this, and then over here we add whatever parameters we want. So like for example, in this case, maybe we would have like previous health in order to know the previous health before the player was damaged. And then over here on the event handler, we use generics and we pass in our custom type just like this. And then over here, when we invoke the events, instead of event args.empty, we just construct a new object of our type and add whatever data we want. So yep, just like this. And again, on all these other ones, of course, we need to remake the function signature in order to perfectly match. And again, this is something that Visual Studio does by default, so just do plus equals, and it's automatically going to write with the perfect event signature. And over here on this one, in order to access that data, that is going to be over here on the second parameter. So we can access E, and then inside we've got the previous health, and we can do whatever we want. Also, one of the first things we saw is over here, if we do not add this null check, if we don't, then this is actually going to throw a null reference exception. So you always need to check for null. However, there's a special way to make this code a little bit more compact. So you've got the event, and again, just like this, going to fire off null if we have no listeners. So what we can do is we can use what is called a null conditional operator. I'm going to cover these in more detail in the advanced section. But basically, we can just add a question mark. And basically, this will mean that the code to the right side, this code will only run if the code on the left side is not equal to null. So we can do the question mark and then call invoke, which is basically going to invoke the event. And just like this. So again, the question mark basically means that it's only going to continue executing code to the right if the code on the left does not equal null. So if this one is not null, if we do have listeners to our event, then we are going to invoke the event. So instead of having a normal test for null, usually with events you have this kind of syntax. So you just do a null conditional operator and call invoke and invoke that event. Now, one of the best things about events is what I mentioned already about code decoupling. That truly is one of the magical powers of events. It's how the event publisher does not know and does not care how many listeners there are to that event. It simply fires off the event and does not care what else happens. Then all the listeners, if there are any, they will listen to that event and do whatever logic they want based on that event. This is really a crucial thing about events. Decoupling your code as much as possible is one of the best rules you can follow in order to write better clean code. And like we saw, this is especially great when games when working with the UI. Usually you want your UI to display your game logic, like for example the health of some kind of tower. You want some kind of visual for it, but you also do not want the tower itself to be dependent on some kind of visual. In theory, your game should work entirely without any UI. And by using events, this is really simple. You can just make it so, for example, over here, the tower class just fires off some kind of event, and then maybe we do and maybe we don't have some kind of external display on top that displays some data based on that event. If the UI exists, then great, but if it doesn't, then the tower works just exactly the same. So events, as you can see, are extremely useful in helping you write better, more performant, and more decoupled code. Definitely make sure you fully understand them, which if you fully understood everything in the delegates lecture, hopefully you managed to quite easily understand this lecture. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn all about generics. This is yet another really powerful C# feature. This one lets you write code that can be used with a multitude of types. Okay, so let's learn about generics, and we've actually already seen them in action in a bunch of places. For example, quite a long time ago we learned about list, and the list, this type requires putting another type within those angle brackets. This right here, for example, a list of int, this is what is called the generic. The list type works with generics, which means it can work with any type. So we can make a list of ints, we can make a list of strings, we can make a list of program types, and so on. If it did not have generics, then we would need to create a separate list class for every single type we wanted to use it with. That would definitely not be very fun, not very easy to use. Whereas with generics, we just define the list class just once, just one time, and then that class can work with any type we want. Also, same thing when we saw the delegates. So we saw, for example, the action, and we saw this one has all kinds of parameters. So we can have an action that takes in a parameter of type int, we can have a type string, we can have a type bool, and so on. Same thing for the func. So again, there's no need to create a specific action class that works specifically with an int, another one specifically with a float, and so on. The action class itself, that one is made to work with generics. It takes a generic t type, and that type can be whatever you want. Now, one of the best practical examples of how useful generics are is actually my grid system playlist. I've built a ton of interesting systems and games on top of that base system, and the reason why I could do that is because the grid system itself, that one is made to work with generics. Here is that class, the grid class with generics. Here it works with a generic type that I named tGridObject. So I can define a specific grid that works with a specific type. Again, it could be something simple like an int, a float, bool, and so on. Or it can be a specific custom grid object class that I define. And with that grid object, I can place whatever custom data I want, and the grid system will work perfectly with it. So I don't need to make a brand new grid system for every kind of thing that I want to do with a grid. I just use the exact same grid system for any type, and by writing this class using generics, by doing that, I managed to reuse this base class and build all those complex systems that I made in all those videos. So how we make a generic class is actually really simple. We just write the class name as usual. For example, let's make our own custom list. So let's make a class, let's call it myList, and then we put our angle brackets, and inside here we give our generic type of name, and technically you can give it whatever name you want, there's no rules here. However, usually the convention is to name this t for type, and alternatively, if you have multiple types, the convention is to use t and then perhaps a number, so t1, t2, t3, so this is what the action uses. Or alternatively, if you want a more descriptive name, usually, once again, you would still start the type with t and then pass in something like, for example, t-unit. Another example of generics that we've also already seen is the dictionary, and if we look inside the dictionary, yep, this one named the generics t-key and t-value. So yep, you can write whatever you want, but over here, let's just write a t, so just like this. So here we have our class with a generic type, and now inside of this code, we can use the type t. So for example, let's make a public field of type t. So yep, just like this. Now importantly is how t doesn't really exist. We don't have any class named specifically t. T is really just a name that we defined. This can be whatever class we're going to use it with. So when we use our myList with of type int, then this field will be an int field. So this is our basic class, and now up here we can make a new, let's create a new myList, and then for type, let's go with int, just like this. So this is a myList of type int, and over here we can go inside, access the field, and yep, note how this field is indeed of type int. And yep, so this does work. Then for example, let's say we want this class to work with bools. Again, since we are using generics, we don't need to make another class definition. We can just go up here, make another myList, in this case of type bool. Let's name it by myList, and then do a new int of bool. And now we can go inside, we can access the field, and yep, this one is now a field of type bool. So over here we have two instances of our class, and each of them is working with a different underlying type. Then in our generic, we define our type t. We're using it over here in the field, but we can also define some kind of functions. For example, let's make a private void my function, and we can receive a parameter of type t. Or alternatively, we can make it return of type t and take in no parameters. Also, by the way, one quick tip, since over here we do not know what type t is going to be, since we don't know that, then for example, we cannot return null. This does not work. And the reason why it does not work is because t technically could be a non-nullable value type. Like for example up here, when we are creating our list of ints or bools, these are not nullable values. These are value types, not reference types. So because of that, over here we cannot return null. So if you do have some kind of logic that is meant to return a default value, instead of returning null, instead of that, you can use the keyword default, And this will return either null on a reference type or the 0 equivalent on some kind of value type. So for example, let's do this. Let's make it public, and then up here, let's call it. So let's call my function. Let's put a right line on this. Let's see what default value is for both of these. So let's see. And if there it is, the default value for an int is 0, default value for a bool is false. Then on the generic definition, over here, like we saw, we can already define more than one type. So we can define T1, T2, T3, and so on. We can do this, and then we can use different types in our code. This works. So here we have our generic class, but we can also use generics without making an entire class generic. We can have just a single function. So over here, let's make a test function. And on the function itself, let's make that function work with generics. The way we do it is really the same thing. So after the function name, we put the angle brackets, then some kind of generic name. And now we can use this type in any way. Like for example, use it over here for a parameter, or we can use it for the return type. And yep, everything works exactly the same. Over here, let's do a console.writeLine. Let's print out p. And for example, up here, let's call out this one. And we can call in with an int. And yep, this works. We can call in with a string. And yep, it also works. Call in with a char. Yep, this works. Call in with a boolean. And yep, this also works. So here we have a function. The function was defined with generics, which means that we can run this function with whatever type we want. Then you can also make structs that use generics. So instead of a class, this can be a struct. And yep, structs can also use generics. Another one is also on interfaces. So up here, we can define an interface, my interface. And on this one, we can also use a custom type. And then we can use this type, like for example, some kind of function that returns of type t. Yep, this is also valid. So lots of use cases for how you can define generics and how you can use them. Another extremely useful thing we can do is simply apply some type constraints to t. Right now we have no constraints, meaning this can be used with any type for the generic. It can be ints, bools, some kind of custom player class. It can be literally anything. Now let's say, for example, we want this one to only work with classes. For that, we can go over here into the class definition. And afterwards, we write the keyword where, and then our generic type, so in this case t, and then put a colon, and then let's say, for example, class. Meaning that this type MyList can only be used with a t type as long as that type is of type class. So like for example, here we see some errors because ints and bools, these are not classes, so we cannot use with those. We need to make some kind of class for some kind of player. And now up here, we can make this of type player. And yep, now this does work. And again, the issue that we saw a while ago on how we cannot return null from this one. But if we do enforce that t has to be of type class, classes can always be null, so now we can indeed use null here. Then another interesting constraint is, let's say for example, we want to construct whatever type we use here. And right now, if over here on this function, if I try to do new t, if I do this, nope, there's an error. Again, same thing, we cannot do it because we have no guarantee that whatever type we use here, whatever type we use has some kind of constructor. In order to make that work, again, we can apply another constraint. In this case, this one is named new, just like this. So now we can use this class with any generic type as long as that generic type is a class and has a parameterless constructor. Which over here, the player by default has some kind of parameterless constructor. So yep, this one is perfectly valid code. And over here, yep, we can do new t in order to construct a brand new player. For example, we can put this on that one, and this one is going to construct a new object of type p, which in this case is going to be the player. So when we run this, it should say something of type player. And if there it is, it's done like that. There's a bunch of really useful constraints we can apply to our generic type. There's a great list on the C# docs. We can see how we can force t in order to be of type struct, of type class. We can ensure that it is a non-nullable type. We can ensure that it has a parameterless constructor. Or one of the most useful ones are simply these ones, basically requiring t to extend some kind of base class or implement some kind of interface. And all of these work on a class definition, but also over here on just a single function. So again, where t is a class, and now it ensures that we can only call this function with a type that is actually a class. And when using the one that enforces that it extends some kind of interface, for example, let's make a function get attack winner, and let's receive two types, t1 and t2. Or actually, let's give it proper names, so t attackable and t defendable. Then we receive those. So we can enforce that t attackable does have to implement the I attackable interface. And we can enforce that t defendable has to implement the I defendable interface. And now since we've applied these constraints, because of that, now we can assume some things about these types. For example, we can go inside our attackable object and we can call get attack points. Then we can go into the defendable and call the get defense points just like this. Now with this, if we had a player type that implements both these interfaces and a unit enemy type that also implements both of them, if so, we could call this function and pass in either two players or a player and an enemy or two enemies. And all of this logic would work because all of them match the perfect generic constraints that we have. So that means that this function, this single function, is really adaptable and can be used with a ton of different types. Whereas if we were to remove these, then nope, we cannot access these functions because we have no guarantee that whatever types we use here will actually have these interfaces. And generally, one of the best benefits of generics is how they make your code type safe, meaning they help you avoid errors when using incompatible types. For example, let's say we have some kind of resource, so we have a type for gold, a type for wood, and then we have an inventory class that takes in a generic type. So then up here, we created different inventories, one for gold, one for wood. If we go inside the gold inventory, and we try to add, and let's try to add some wood. If we do this, then nope, obviously this one throws an error. This is how generics help us by making our code type safe. If we make an object of a type and we define that this one only works with gold types, if so, then we cannot add some wood on there. The type itself is going to be forced as soon as we create the object, and we cannot break that rule. Alright, so those are generics. It's another extremely useful C# feature. I use them all the time. They are super useful for making your code really adaptable. So definitely make sure you fully understand this and make sure you use it whenever you need to. This is really powerful, but also for beginners might be a little bit confusing. So if you feel a little bit lost, maybe go rewatch this lecture one more time, maybe go inspect the demo, and definitely make sure you do all of the interactive exercises. This is a really powerful feature you definitely must know about. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn about constants and the read-only keyword. Okay, so normally we have regular variables, like for example int age, and a variable, just like the name implies, the value inside of it can change. They're intentionally supposed to be modifiable, so over here I can set it to one value and then set it to another value. Yep, this works. But sometimes you really don't want something to modify. Some things are meant to have some kind of fixed value. Like for example pi, it has a fixed value, and in C# you can actually see it with math.pi. Yep, there it is, 3.1415926 and so on. And note over here how this one is a constant, meaning it always has this value. You cannot change to something else. So if here I put it to just 3, nope, this does not work. I cannot assign this to anything else. It's a constant, meaning the value is always going to be fixed. So I need to define some kind of field for something where the value should never change. Like for example, some kind of float for some kind of player speed. If we set it like this, then this is a perfectly regular field, so we can read it and we can modify it. In order to make it a constant, we just go here and we add the keyword const. And if there it is, and now we can use this field whatever we want, and this is always going to have this constant value. We cannot modify this. By the way, for the name, like I mentioned in the naming rules lecture, usually constants are uppercase, snake case. So everything is uppercase and split all the words with an underscore. And of course, since constants cannot change, then we have to assign some kind of value. So if we define something as constant, we have to define it with some kind of value. Okay, so yep, this is our constant. And constants are also basically static by nature, meaning they do not belong to any instance of any class, they belong to the class itself. So for example, over here, we're working inside the static main function, and usually we can only access static members. So if this one is just a regular field, if it is like this, then over here we cannot access the player speed. We cannot access it because this one is not static, but by marking something as const, that makes it essentially static by default. So over here, we can do console.writeLine, we can print this out, and up here we can indeed access player speed. Also importantly is how constants, they are set at compile time, meaning the value has to be evaluated and defined during compilation, not during runtime. So that means constants are also somewhat limited in what types you can use with them. For example, we cannot make some kind of class. Let's make a class player. So we have this, and now up here we cannot make a private const of type player for the player. We cannot do this because we need to assign a value. And if we construct a brand new player, nope, this does not work because this line would only run during runtime and not during compilation. So for the most part, const can only be used with the built-in types, so things like float, bool, we can use string, and so on. However, classes, custom classes, or even default ones like for example object, these cannot be const. So constants have a bunch of limitations, but for example, if we inspect the vector3 struct, so let's go inside of this one, so let's right click, and over here let's go to definition. So here it is the vector3 struct, and if we scroll down, we can see it has some things that look kind of like constants, like vector3.0 or .1. But again, a struct cannot be constant, so note how these are not constants. Instead, these are statics, and this is actually a property and only has a get and always returns the same value. So this is one of the workarounds you can do if you're trying to make a constant of a type that cannot be constant. Alternatively, there's another really interesting workaround. You can build something similar to a constant by using the keyword read only. So let's define a field. Instead of making this a constant, let's make it a read only. And if this one now does work, we don't have any more errors. What read only means is that these fields cannot be changed after they are set. So if we try down here assigning it to a brand new thing, nope, does not work, this throws an error. So if you mark something as read only, it can have some kind of object type, but it must be set either over here directly in the declaration, or it must be set in some kind of constructor. This one works with any type, so it can be custom classes, or it can also be the built-in types like int and so on. It can still be useful to use read-only instead of const even for these basic types. Like for example on the player class, over here let's say each player would have a different kind of maximum health, so they would have a private read-only for the health max, and then on the player constructor we could receive a certain health max, then assign the health max onto this one just like this. Meaning that this would sort of act like a constant, meaning we cannot change it afterwards. But this way, by using the read-only tag, basically we can set it to a different value and does not have to be set directly at compile time. So that's really the main difference between these two. For any data that you never want to change, and any data that can be defined at compile time, for those you can use const, and if not, you can make it read-only. Once again, remember the main goal behind writing good clean code. The main goal is minimizing complexity, and the best way to do that is minimize how many things can change. So if something is never meant to change, then either just make it a constant or read-only. Doing that will help you make your code much easier to understand. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn about exceptions, as well as how to handle them and fire custom exceptions. Okay, so exceptions, these are really errors. We've already seen them a bunch. For example, here's some code that is going to throw an error. So I define an int a variable with the value 0. And then I just do 1 divided by a, so 1 divided by 0. You can never divide by 0, so this is going to throw an error. Let's try running. And if there it is, right away, divide by 0 exception. So when you hear the word exception, think error. Now, if I were to write some logic after this, like for example, let's say console.writeLine, let's print out something. So let's try running. And nope, that message does not run. As soon as the code gets to the exception, it stops executing. That's where exceptions are meant to do, but sometimes you don't want to happen. Usually if something goes wrong, you want to know that something went wrong, but then you also want to handle it. So usually you don't want to have unhandled exceptions. So the way that we can handle exceptions is with a try block. Meaning we write the keyword try, and then put a code block, and inside that code block we put whatever code might fire some kind of exception. And then to make this valid, we need a second piece of code which is called the catch. But first, let's run it just like this. So this is still going to throw an exception. This is still going to throw an error dividing by 0. But now let's see if this line does run. And if there we go, it did run, and we do not have our exception. Now technically the exception still happened. It really just happened silently. For example, if we were to put a log over here inside after our exception, just say something, and we're going to see how this log does not run. And if that one does not run, only this one down here. That's because this line is still throwing an error, so it stops executing anything afterwards. But since we put it inside a try catch, because that as soon as the error happens, basically it's going to drop into after the try. But like I said, usually you want to handle exceptions, not really just ignore them. So for that, over here on the catch block, we can add some parentheses and we can put some kind of exception type. For a general catch-all, you can just use the exception type, then give it some kind of name like exception. And now inside of this object, over here we have a ton of data related to that exception. We can see the message, the stack trace, the source, and so on. So for example, over here, let's do a console.writeLine. Let's print out the exception.message. And then let's also print out the exception, let's say the stack trace. Okay, let's see. And if there it is, that one did find an exception. So attempted to divide by 0. And found in our program on line 19, which yep, it is exactly that one. So yep, with this we are catching our exception. And you can also add multiple catches. You can add different ones to test for specific types. Like for example, let's add another catch. And for this one, let's test for the specific divide by 0 exception. Except one important thing about having multiple catches is how it's going to go from top to bottom. And since every exception always extends from exception, this one is always going to run first, so this one is never going to run. So let's put the specific one before the generic one. Another thing, if we don't need any data inside of our exception itself, if we just want to test out what type happened, if so, then we don't need to give it any kind of value. So just like this, it's going to work. It's going to catch an exception of this specific type. So let's do a console.writeLine. Let's print out our divide by 0 exception. Okay, let's see. And yep, exactly like that. So we have our divide by 0 exception, and then the code continues running downwards. Okay, great. Also, another thing you can add is after the exception, you can add the when keyword, and over here we can test for some kind of condition. So for example, when exception is of type divide by 0 exception. So if we do this, then yep, same thing. This code is going to run pretty much the same thing as this one. So it gets an exception, stores it in here, and tests out if it is this type, and if so, it's going to run this one. So here we have a try and then a catch, but there's yet another block that we can add, and that one is the finally. You add this one after the catch, and basically over here, the code inside this code will always run. So let's do a console.writeLine, and let's say finally. And for example, up here, let's make sure it doesn't go inside of this catch. So let's put when exception, let's make it of the type that isn't going to happen. So let's say, for example, the argument out of range exception, okay, like this. So this one is not going to run, but we're going to see how the finally is still going to run. So the finally always runs no matter what. So like this, if we run, yep, we do catch our exception, then the finally runs, and then the hello there. So now you might be thinking that the finally works exactly the same thing as down here, so we could just put this in here and it would work. But one difference is on the finally. Over here, when we catch our exception, let's say for example we want to end this function, so we call return, and let's see what this does. And if we call return, meaning this function is going to terminate, so it is not going to continue running afterwards. However, even though we are returning, we still get the finally message. So this finally block runs after the catch every single time. So usually the finally code block, this one can be really useful if you need to do some kind of cleanup code. For example, if over here on the try you were opening up some file for reading, you want to make sure that if you do open up the file, even if there's any kind of errors, you want to make sure you do clean it up. Also, by the way, you don't need to add the catch, so you can just do a try finally, and yep, this also works. Okay, so this is how we can catch exceptions. Now to throw them ourselves, we can also do that. For example, let's say we have our custom class for our player, and then over here in the player constructor, and then let's make a test function. And on this function, we want to spawn some kind of exception. So the way we throw an exception is with the keyword throw, and then whatever exception we want. Like for example, let's just throw a regular exception. So just like this. And for this one, you can open it up just like this. So just make a regular empty exception, or you can give some kind of message. So for example, player exception. Okay, so yep, just like this. So now up here, let's remove our previous testing code. And now let's create a new player and go inside the player and call test function. Okay, let's see. And if there it is, that one did fire off a player exception. So if you want to throw your own exceptions in your own code, this is how you do it. Just use the throw keyword. And then you can even make your own exception type. For example, let's make a class. Let's call it invalid player name exception. The only rule is that we need to extend from exception. So just like this. And over here, instead of spawning a general exception, we can do our regular one. So just like this, let's run our code. And if there it is, exactly like that. So exception of type, and of our type, invalid player name exception. Also, one more thing is, for example, over here, if we do a try catch, sometimes you might be running this inside some kind of function, and that function might be calling some other function that might throw an exception. So essentially, you've got functions within functions, and sometimes you want to basically just keep throwing the exception all the way up the call chain. So if you want to do that, you can just call throw, just like this, and this is basically going to rethrow the exact same exception. And if there it is, in this case, since we are throwing once again on the main, then we end up with a regular exception. So by using the try catch to handle exceptions, you can make your code a lot more robust. For example, when making a game, you really never want the game to crash. If something goes wrong, like for example the player somehow has 0 items and because they divide by 0 exception, if that happens, you really don't want the code to break, you don't want the game to crash. So if that happens, you probably want to have that in some kind of try catch block in order to catch the exception and handle it in some kind of graceful way. And especially when working with some external code, like for example contacting some API on some web server, for those you really want to add try and catch in order to make sure that your program continues running correctly regardless of what the server replies. Hello and welcome, I'm your Code Monkey. In this lecture we're going to learn about enumerators, how to implement IEnumerable and IEnumerator. Okay, so something we've already seen several times is doing a simple for each on a list. So we can do a list of int, some kind of int list. Then we just construct a list and we can do a for each int I in the int list. And yep, this works perfectly. So we can do a for each and cycle through every element in our list. But then if we try doing a for each on some kind of custom type, so for example here, let's make a player, new player, and then let's try doing a for each on this player. And nope, this does not work, we have an error. Like it says here, the for each statement cannot operate on variables of this type because player does not contain an extension definition for get enumerator. In order to make the for each work with custom types, for that we need to make our custom types enumerable, so let's learn how to do that. For example, let's define a class for holding a single stat, so some kind of name and value. So just name it stat, and inside just have a string name and just an int for the value. And then let's make a class to hold a bunch of player stats. So class called player stats. And over here, for example, let's have some fields of type stat. Let's say for dex, for strength, wisdom, and so on. So yep, just like this, let's just construct these objects. Okay, so yep, just like this. And now let's say that we want to do a for each, and we want the for each to work on our player stats. So basically we want to be able to cycle through each one of these stats individually. So to do that, the first thing we need to do is over here, let's implement an interface. Let's implement the IEnumerable. This one takes in a generic. So let's say our generic type is going to be of type stat. Yep, just like this. So now we can implement this interface. So it requires us to implement those two functions. This requires us to do something that constructs an object of type IEnumerator. So enumerable and enumerator Those sound similar, but they are different. So let's make a class that is going to be our enumerator. Usually for that, we build it as a nested class. So up here, let's make that. So the player stat enumerator, and we're going to implement enumerator, and again, also of type stat. Then let's see what we need to implement on this one. So over here, let's select, and then over here on this little light bulb, let's implement this interface. So yep, there you go. Now we need to implement all of these. And over here, we just need to handle some kind of index. And based on the index, we're going to return either of these ones. So that means we also need a reference to our player stats object. So let's make a constructor here. And on the constructor, let's receive our player stats. So you have this, let's store it inside. So just like this, we have our player stats. And then we also need some kind of index in order to know the move next, the current, and so on. So let's do an int for the index. And for the index, let's default it to -1. The reason for that is because the for each is going to call the move next before it grabs the current. So let's start off at -1, and then on the move next, that's pretty simple. So let's just do index ++. Then since we have just 3 stats, so this one is going to be index 0, 1, and 2. Because that over here, if the index is bigger than 2, if so, let's just loop back to -1. Then this one needs to return true if the enumerator was successfully advanced, and false if it has passed the end of the collection. So we can just return if the index is not -1. Okay, that's our move next function. To dispose, we don't really need to implement that one. And the reset, we can just set the index to -1. So what's important is over here the current. This one is a property, so let's go ahead and implement this property. This one is going to have a get, and on the get, we're simply going to test out our index. So let's do a switch on our index. Let's add a default, and let's add a k0. So k0, let's return, go inside the player stats. And on index 0, let's return, for example, let's go up here. Let's see, so the first one is dex. Then Ks 1 and 2. For this one, let's return strength, and this one, let's return wisdom. Okay, so yep, so that's the current. And over here for this other current, we can just do a pass-through onto that one, just like this. So yep, this is our enumerator class. So we receive our player stats, so we have the original object. We have some kind of index. Then on move next, we just increase the index. And on current, we just grab the value based on that index. So now here on the get enumerator, we only just need to return a new player stats enumerator object, and on that one we need to pass in this. So just like this, and on this one again, same thing, we can do a pass-through function. So return get enumerator. Okay, so now finally up here we can let's construct an object of this type of our player stats. Let's construct a brand new object. And now, yep, now we can do a for each on that one. This one is going to return of type stat in our player stats, and let's just do console.writeLine on our stat. And just to be able to see that, let's go inside our stat. So inside this one, and let's just override our toString, and let's return the name and then the value. Okay, so just like this, let's test and see if our for each is working and if it's going to go through all of our various stats. And if there is exactly like that, so it did a for each through our custom type, it found dexterity, strength, and wisdom. Alright, awesome. So this is how you make your custom types work with a for each. You just need to implement both of these interfaces. Just do that, do some basic logic in order to grab the current value. And with that, you can then use your custom types inside a for each. By the way, alternatively, for this specific use case, where we have a fixed number of elements that we want to cycle through, for this, a simpler approach is just on the enumerator. We can just do a yield return. So over here on the function to get the enumerator, instead of creating a brand new enumerator, instead of defining this entire class and creating all of that, if we just have a fixed number of elements, we can type in the keyword yield, yield return, and then whatever we're going to return. So let's say return dex, then do another yield return for strength, and another one for wisdom. Basically, what this is going to do is this function is actually going to be called multiple times. So by making something enumerator and using yield return, by doing that, this function is essentially going to store its state. So the first time that we call this, it is going to return dex. The second time we call it is going to return strength. And the third time we call this, it is going to return wisdom. Let's test this. And if it works exactly the same, we have our 3 stats. So basically, whenever you have a dynamic number of elements, so if inside your custom type you have some kind of list, some kind of collection, for that you can define an entire enumerator and write all of this code. But when you have just a fixed number, just a bunch of simple stats, a bunch of simple elements, for that, just using a simple yield return, this one is much easier. Also, since we're on the topic of enumerator and enumerable, let me mention one Unity-specific thing, which are coroutines. If you're just using C# without Unity, then don't worry about this part. But Unity basically has coroutines, which is a way to run logic across multiple frames, and specifically it works with enumerator. In order to make a coroutine, we make a function that returns enumerator, And then over here, you can do whatever logic you want. Then when you want to split the logic, you can do yield return. And then Unity actually has some nice built-in functions. Like for example, we can do yield return, wait for end of frame. This is basically going to wait for the end of frame before running the code down here. Or for example, we have wait for seconds. This is going to wait for a bunch of seconds before continuing to execute the code. For example, let's wait for 3 seconds. Then let's do a debug.log and say something. So let's do debug.log before and after. Okay, so this is going to basically run some code after some time. So this is a great way to handle timing-based logic in your games. With this, we have a coroutine. And now to start, we just need to be working inside a MonoBehavior class. And of course, this script needs to be attached to a game object. So then we do this, and let's make a start. And over here on start, we just need to call the function start coroutine. And this one takes our enumerator, so let's just call my coroutine, just like this. Yep, so this is going to start running this coroutine, so we should be able to see this log immediately, then wait 3 seconds and then see this log. Okay, it's running, there's the first message, and after 3 seconds, we should be able to see, yep, there it is, the second message. Alright, awesome. So these are coroutines, which is a Unity-specific thing that works with enumerator. Now personally, I must say I'm not a big fan of coroutines, simply because I don't like this pattern that they force you to use. It feels needlessly convoluted to me. You need to be working on a MonoBehavior, you need to call start coroutine, you need to make a special function that returns enumerator, use yield return, and so on. So personally, I'm not a big fan of this huge pattern. Personally, I prefer using super simple float timers, but coroutines work great, so if you like this, then definitely go ahead and use them. Okay, so those are enumerators. It's how you can make your custom types work inside a for each and various other settling logic. For example, things like link, which we're going to cover later on in the advanced section. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn about namespaces in C#. Okay, so namespaces, this is one of the main ways you have of organizing your code. Think of it kind of like folders for your code. For example, you would have some kind of folder for your game logic, another one for some AI logic, another for the UI, and so on. Basically, it helps you keep things organized. And actually, we've already been using a bunch of namespaces. Up here, all of these using statements, these are all namespaces. For example, the console class that we've been using, this one exists inside of the system namespace. We can access it by writing using system up here, and then we can access the console class. Although actually, when making a console app, the system namespace is included automatically, so technically you don't need to explicitly define it. But in most cases, you do need it, so you do need to add using some kind of namespace. And also over here on this template, when we created the brand new project, it automatically created our program class with our main function, and it put it all inside a namespace. Now I should say, technically you don't need to have a namespace, so if I get rid of this and this, yep, this still works, this is perfectly valid code. Basically, when it compiles, it will simply place this class in the root namespace. To create a namespace, you really just follow this simple syntax. So you write the keyword namespace, and then whatever you want to name your namespace. Also, namespaces, they can have nested namespaces. For example, inside the system namespace, there's a whole bunch of stuff, like for example, the IO namespace. This is the one that contains a bunch of classes related to input and output and so on. Then here is a script inside of Unity. So Unity normally has most of their things inside the Unity engine namespace. For example, MonoBehavior, this one exists inside of Unity Engine. Then if you want to do things inside of the UI, then you would use using Unity Engine.ui. So basically, all of the classes are nicely organized in a namespace that makes sense for them. You can also make nested namespace yourself. You can just write some kind of name, then add a dot, then add another name, and so on. Then one big benefit of namespaces is avoiding name conflicts. For example, let's say I want to define a player class. And now let's say I want to define a completely separate class, but I really do want it to have also the same name, so also another player class. Since classes have to be unique, this does not work. Here we have an error that it says that this namespace already contains the definition for our class named player. And right away, this is also giving us a hint as to what the solution to this problem is. The solution is simply put it in another namespace. So namespace, I can give it whatever name I want. Then I can place this class inside of that namespace. And up here, I can use either of them. So I can use player, and this one is referencing this one down here, this one inside of this namespace, or I can go inside the CodeMonkey namespace, access player, and yep, with this, now I'm referencing the other one in the other namespace. Then another common issue is sometimes you have a conflict that the compiler cannot resolve. For example, over here, I added using system and using Unity Engine, and now I want to use the random class. But the problem is that there is a random class in both Unity Engine and inside of system. So the two namespaces that I'm using up here, they both have a class with the exact same name. So basically the compiler over here does not know which class I'm referring to. So to solve this problem, either we get rid of one of the using statements, and yep, this works, so now there's no more errors. However, that won't probably break any other place where you're using classes from that namespace. So in this case, for example, if I add the serializable attribute which exists inside of system, by solving this problem, I now cause this problem. So to solve these kinds of naming collisions, usually the simplest thing is to just write the full name. So for example, up here on this one, I can write system, and even though this one works and this one has no problem, or alternatively, I can just add the using system up here. So this one no longer has an error, but this one does have the error. And over here, I can just write the full name unityengine.random. And yep, like this, the compiler doesn't have any questions. It knows that I'm trying to use the random class that exists inside Unity Engine. Another thing you can do with namespaces is simply using an alias. So over here, we can say using, then give it some kind of name like Unity Random, and then say equals unityengine.random. So basically, this one is now an alias to this. So down here, instead of using all this, we can use this. And if there you go, it does work. This can be quite useful when you have a really complex project with some super long names. When that happens, using the alias can really help simplify your code. Okay, so that's namespaces. It's a simple yet very useful C# feature. As your project grows more and more, they become more and more useful. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to learn about the singleton pattern. In terms of game development, this is probably the most useful pattern, and also one with a lot of pros and some cons, so let's learn about it. Okay, so the singleton. Like the name implies, we have just a single instance of something. In this case, we have a single instance of some kind of class. So for example, we have some kind of game manager class. And over here, the way that we have just a single instance is usually with some kind of static field. Again, static means that the field belongs to the class itself and not any instance of that class. So usually we make it private, static, let's call it of game manager. And for the name, we call it instance. Instance is usually a common name used for singleton, although sometimes it's literally named singleton. So either one. So here we have our private field, and we made this private specifically for one very good reason. The reason is because this class should be the only one that is responsible for creating the singleton instance. Other classes should only be able to get it. So the way that we're going to expose this is by using a public property. So let's make one also going to return the type game manager, and property usually starts by a Pascal case. So we've got our property instance, and over here on the get we just return our instance. And then for the set, for this one, again, like I said, the instance should only be set by this one. So for that one, let's make a private set. And on private set, just set instance equals value. Okay, yep, so just like this. Basically here we have a field that anyone can access, but only this class can set. Now for actually creating this singleton, let's first cover the bare bones C# method, and then I'll cover the Unity specific method. So singletons usually have what is called lazy instantiation. This means that the instance is created only when it's needed for the first time. And in order to do that, we just put that logic over here on the get. We just check if our current instance, it is null. If so, that means we have no instance. And if so, then we just create a brand new one. So we create it and then we return it. So basically this means that as our program starts, there will be no singleton instance. And then the very first time that we use it, it will actually create that singleton. Also, as a general rule, singletons usually have private constructors. So if you define some kind of constructor, it's going to be private. That way, any code up here cannot do new game manager. Nope, this does not work because the constructor is private. Again, that's because the singleton is meant to be the one that is responsible for creating the singleton instance. So the way that we use this is actually very simple. Alternatively, another way of implementing the singleton pattern is without lazy instantiation. So an alternative would be to expose the constructor and then just check if the instance, if it is null. If so, set the instance to this. So this is another way that the singleton pattern could be implemented. But again, usually you have some kind of private constructor that only this one calls. And over here, we don't even need any kind of set because only that one is going to be set. So yep, this is the basic C# singleton pattern. And now in order to use it, it's actually real simple. We just access the static property. So we just go inside the game manager, access the instance just like this. So let's do a console.writeLog. And now we didn't create any kind of game manager object. Up here, this code is not creating anything, does not know anything about any of that. It just knows that it's accessing the game manager, accessing the static instance. That's it. So if we test this, and if there it is, then we do have an object of type game manager. So just by accessing the static instance, it automatically created that object and returned that instance. Then over here, we can do whatever we want. So for example, some kind of public test function. So we have some kind of function that does something. And then up here in our code, we can go inside the game manager. We can access the static instance. We can call test function. And yep, this will indeed work. Also, by the way, note how just one instance is created. So up here, we are accessing one instance in here and then going through this one to calling the test function. So we're accessing this property twice, but when this code runs, obviously since instance is only going to be null just once, it is only going to create one game manager. So no matter how many times we call this, we end up with just one single instance. And since we made the constructor private, because that, nothing else can construct this object, so we know for a fact that this class will only have a single instance, making this the singleton pattern. As for the benefit of it, the benefit is that it's really super simple to use. Just by accessing the class itself and accessing some static instance, just through this we have a reference to whatever object we have of type GameManager. So we can call functions on this class, we can do any kind of thing. We don't need to keep track of any kind of GameManager reference. So for example, if we had some kind of class of type player, and then the player does something, it like adds some kind of score, so the player would end up killing some enemy or something. Over here, the player does not need to store a direct reference to the game manager. We can just go inside game manager, access static instance, and then we would call some kind of add score function. By using this singleton, we have our instance of the game manager real easily accessible from pretty much anywhere in our codebase. And now that we've seen the singleton over here, the bare bones C# singleton, let's see how to make it in Unity. In Unity, it's a little bit different since Unity components have to extend mono behavior, and one of the biggest limitations of that is you cannot access the constructor directly. So in Unity, you simply make a regular script, extend mono behavior as usual, then that script is attached to some kind of game object, so all pretty standard. And over here in the code, here personally this is the only scenario where I use properties. And here I don't even use the backing field directly, I use the auto-implemented property. So I make it public because I want to have a public get. Let's make it static of type game manager. Let's call it instance. And then this one has a public get and a private set. So yep, just like this. So this field has the perfect accessibility that I want for the singleton. So any class can get it, but only this class can set it. And then on the Unity's standard awake function, over here on this one, just set instance equals this. And yep, that's really it. The awake is going to run when this game object runs, and when that happens, it is going to assign the instance into this. Now, this one technically isn't enforcing the singleton rule. If over here in Unity I duplicate this object multiple times, then I'm going to end up with multiple game managers. And the one that is going to be set on that static instance is going to be whatever is the last one that runs. So for this problem, normally the only thing I do is I'm really just careful enough to only make one object that has the static script that I want. But if you want, you can also add some proper safety checks. One way to do it is over here before assigning the instance, we check if instance is not null. If so, that means that this script already exists and the instance has already been assigned. If so, this should not happen, so over here we can probably just fire off a log error. So if over here I duplicate this object and I try running, if there it is, we have a log error and it tells us what the issue is. We can see it's on the game manager class. Then you can either manually fix this, so go into the hierarchy and delete the second one, or over here on the script itself, we can destroy this game object to make sure only one is kept alive. So for example, instead of that, let's just destroy this game object and then call return so the rest of the code does not work. So if we run this, and if there it is, we have our error, because we do still have two game managers. However, if we're only in the hierarchy, yep, the second one was indeed destroyed. Now, this singleton pattern is extremely useful when you have some kind of class of which there is only meant to ever exist just one single instance of that class. For example, in games, it is very common to have some kind of general game manager, and again, you have just one. Usually you also have some kind of audio manager, some kind of input manager, and so on. Then for single player games, you might just have one player or even just one world. So if you have just one of something, then the singleton pattern is actually really great. It makes a lot of sense and makes it really easy to access that static instance. For example, if your UI code wants to show the player's health, it doesn't need to have a direct reference to the player, it can just grab the singleton reference. Or if your player needs some kind of input, it doesn't need a reference to the input manager, it just accesses the static instance and that's it. So the singleton is great, especially in game development, where you normally have tons of systems that have a single instance. However, the singleton pattern also has some potential problems. If you Google, you will find a lot of people arguing that this is a terrible pattern. Although I should say, usually those anti-singleton comments are always a little bit too extreme. The singleton is a tool, and just like any tool, it can be used or abused. And in general, singleton seems to be worse for regular game development, not game development. For game development, like I said, it does have a ton of benefits that do outweigh many of the possible cons. And in general, if you write some good clean code, you can actually minimize a lot of those cons. Like the main con is simply the fact that singletons are by definition global data. The whole purpose of singleton is to have a single instance of something that you can easily access from anywhere. So because of that, it means that it can have many of the negatives that any kind of global data can have. Your code can easily become really messy with tons and tons of connections between various classes. Since singletons are so easy to use, you might be inclined to use them all the time and make it so that every class pretty much depends on a ton of singleton classes. Doing so ends up with a mess of dependencies. Ideally, your code and your classes should be as decoupled as possible. You shouldn't have a ton of connections. This advice is applicable really all the time, not just in relation to singletons, but singletons make violating this guideline very easy, so that is why you need to be extra careful. And because those issues of classes becoming coupled with tons more classes, Because of that, testing can become insanely hard, simply because in order to test something, if the class you're testing accesses some kind of singleton, then that singleton needs to be created in order to test, and in turn, maybe that singleton then uses yet another singleton and on and on, so you might end up requiring a ton of setup to do even just a basic bare bones test. Another more serious problem is with regards to multi-threaded code. You need to be very careful to make your singletons thread safe, or simply make sure you only access singletons from the main thread. For example, if you use Unity dots to write some super performant multi-threaded code, the simple way to avoid this problem is to do all your logic in tons of threads. Then at the end, after all those jobs are completed, then you do anything that requires a main thread. Like for example, accessing the sound manager singleton to play some sort of sound effect. So singletons can indeed do have some negatives, but they're also extremely powerful and extremely useful. It is a pattern that can be very good when used, but also very easy to abuse. Personally, I use a ton of singletons in all of my games. I just also make sure not to abuse that pattern. I make sure to control how often I use them and limit class coupling as much as possible. So my advice is don't be afraid of singletons, they definitely have their place, but use them properly so they actually help you as opposed to hurt you. Now the singleton pattern is just one of many programming patterns. It is the one that I use most often and I find most useful, so I made this dedicated lecture. Now next one, let's go through a bunch of other patterns that also have their use case. Hello and welcome, I'm your Code Monkey. In this lecture we're going to talk about a bunch of design patterns. Okay, so first of all, what are design patterns? In the last lecture we already covered one specific design pattern, the singleton. These are basically some general, reusable solutions to some common programming problems. The Wikipedia page has a great reference with tons and tons of detail. For example, the singleton pattern that we just saw. This one is a nice solution for the problem of how do you ensure a class has only one instance, and how do you ensure that it has a global point that is easily accessible. That's the entire purpose behind that pattern. And by writing the code like we saw in the previous lecture, that is how we can achieve those rules. So that is a very good solution to that common problem. And within that pattern, we also saw another mini pattern, the lazy initialization. So this is how we made sure that the singleton only gets created the first time that it's actually needed. Another pattern we've actually already seen is the observer pattern. This is a pattern where an observer interacts with a subject to be notified whenever something happens. So yep, this is literally what we already covered in the events lecture. A class subscribes to an event and again gets notified when that event is fired. So using events is essentially the observer pattern. Another common one is the command pattern. With this one, you can basically create commands that can be executed later on. So one common use case for this kind of pattern is making some kind of undo system. So when you do some kind of action, you create a command for the undo action with all the data that is needed to perform that undo. And then when you want to undo, it simply runs that command. So this is the kind of thing that can easily be built by combining a stack with delegates. Another interesting one is the factory pattern. With this one, you basically put the creation of an object in some kind of factory class. And then instead of having every class with a constructor that anyone can call, instead only that factory class is responsible for creating those objects. Again, we also saw a part of that pattern in the singleton pattern, where the singleton itself is responsible for creating the object. So the factory pattern is pretty much just a more dedicated part of this pattern. It can be really useful to limit the number of places from which a certain type of object can be created. Then the object pool pattern, this is a really useful one. This is how you can create a pool of a bunch of objects. And in doing so, it really reduces the impact for creating and destroying objects. Unity actually recently introduced an object pool type that does exactly that. If you have performance issues with spawning and destroying objects, you should definitely be using some kind of pooling. Then dependency injection. This is an excellent pattern for testing your programs. This one uses interfaces quite heavily. It's one of the main reasons why interfaces are really excellent. You can inject different types of objects as long as they implement a common interface. Then the adapter pattern, or simply a wrapper. This is especially great when working with some kind of third-party code. You build a wrapper that only contains the info you care about, and then you don't have to worry about any more of the underlying implementation. So as you can see over here, there are tons and tons of patterns, and pretty much all of these have dedicated pages, so if you want to dig deeper, I definitely encourage you to do so. These patterns were created by some very smart people in order to solve some very common problem. So rather than reinventing the wheel, just being familiar with some of these is really great. But you really don't need to memorize all of these. I highly encourage you to research them just so you know they exist. But don't try to memorize everything in one go. Like with the Visual Studio Shortcuts lecture, this is something that you pick up more and more over time. But definitely do take the time to research these in a little bit more. Like the saying goes, there's no point in reinventing the wheel. Sometimes you have a problem for which a pattern would be the perfect solution, and if you know that pattern, then you can simply apply it rather than having to reinvent a brand new solution. Now for me personally, I normally just use the singleton and the observer pattern specifically. I use those pretty much exactly like they are designed, and then I use various other ones when I need them, even if I don't necessarily follow these strict patterns. So sometimes, for example, I have some kind of factory pattern. I have that where some objects are created only in a specific place, but I don't necessarily create a brand new specific factory class. Then, like I said, sometimes I use something similar to the command pattern, especially in management games to queue up all kinds of actions. And in Unity is all made about composition of various scripts, so technically it is the composite pattern. And I do normally try to compose my complex objects, usually by composing them based on interfaces, rather than just making one huge object with all kinds of logic. So I highly encourage you to research some design patterns in order to be familiar with them, but again, don't worry too much about memorizing them, especially not all of them. I certainly do not have memorized all of these patterns, only a handful of them. Then as you go through in your game dev or programming career, you'll learn which ones you will commonly use as you encounter similar problems. Hello and welcome, I'm your Code Monkey. In this lecture, we're going to see a nice project that incorporates everything we've learned so far in this intermediate section. Although, actually, we've already covered a ton of stuff, and some of it was necessary to get this demo built, which this is actually a great practical example of everything you're learning in this course. This course is all about C#, and C# has a ton of tools and features, but that does not mean you need to absolutely use everything all at once every time. The goal of all this is to use the things that help you achieve whatever goal you're trying to achieve. So let's see the demo. It's inside the Unity project, inside the lectures, and down here at the bottom we've got the intermediate project. So we have our game scene, let's open it. And here is the minigame running. So I've got a player object, I can move around by pressing the arrow keys or WASD. Then down here I've got an inventory with 3 slots, and there are some weapons and some items that I can pick up. There's also some enemies that are spawning and coming to me, so I can approach the weapon in order to pick it up, and I can click in order to start shooting and start taking down some enemies. So as I shoot, they take some damage, they get a health bar that goes down and updates, and eventually they die and they spawn a bunch of money. Then for the money, it's also something that I can pick up, so I can touch it and pick up all this money. I can see the UI is updating as I pick up some more money, and there's a bunch more items and objects. So for example, there's some bombs. Those bombs are also attackable, so I can attack them and I can destroy them. And then I've got the other weapons, so I'm using a pistol, and then I can pick up a shotgun, and down here on the inventory, yep, I picked it up. So now I can swap the shotgun and I can start shooting, and this one has a different shoot. So this one can now shoot multiple bullets at once. And again, I can pick up all this money. And then over there is also a nice little potion. I can pick it up, and again, that's also another item. It's a usable item. So I can use it, click to use it, and if there you go, this goes into some kind of super mode where the player is now moving much faster. So I can move around really fast, and eventually it ends up. And I can select another different one. So let's go back to the pistol. Let's go into that one, speed it up, back to the pistol, shoot that one, and so on. So yep, this is the demo with lots of stuff happening that involves a lot of the things that we've already learned about. There's player movement, there are all kinds of interactions, there's shooting, there's enemy, there's health, there's damage, there's an inventory, a whole bunch of items, abilities, and so on. So as you can see, lots of stuff. Now let's inspect this to see how it all works and how all the elements of C#, how all of them are being used. Although also, before we look at the code, let me make one quick note. Basically, how I built this project is not the absolute only way to do this. You could build this exact same project in a million different ways. So as we're going through it, if you think to yourself that you would build some element in a different way than I did, that does not mean that you're wrong. There's always many ways to achieve the same result, and the way that I built this demo is simply just one way out of the millions of possible ways to build it. So if you come up with a different way to implement the exact same elements, you can definitely be right as well. Okay, so here in the project files, we can see that this demo is quite a bit larger than the beginner demo. There's quite a few more files. That's due to the fact that it is larger than the beginner project, but also due to the fact that the code is much more well organized. There's plenty of small classes that do one thing and one thing only, as opposed to the beginner project where I tried to make it as compact as possible, which meant putting too much logic on the player class. Whereas over here, you can see how each file is actually pretty compact. You can see most of it pretty much just over here on the quick code preview. Most of these files are actually pretty small. So let's begin inspecting this, and let's actually begin with the most complex script of all, the player script. Let's do just a quick overview of this one before we see everything one by one. And right away, as soon as we open this, we can actually already see a bunch of things that we learned in this intermediate section. So right away, we can see a namespace. So all of the code for this project, all of it is inside this specific namespace. And one of the benefits that I talked about namespace is simply the fact of name collisions. And actually on this companion project, note how all the code for all of the various lectures and all the demos, all of it is inside this one project. And I do have a bunch of other demos that also have some kind of player class. But because over here I'm using a namespace, that makes it sure that this player class does not have a naming conflict with any of the other player classes. So that's the first thing, using namespaces. Then by the way, the mono behavior over here. Here we are seeing an instance of inheritance, and mono behavior is really just a base Unity class. Basically, if you want to attach any script as a component in Unity. So for example, over here, if I select the player object and I look in it, yep, it has the player script attached to it. So in order to attach a script onto a game object, it needs to inherit from that class. Then we can also see over here we have the singleton pattern. So we've got a public static player instance with a public get and a private set. And this one, the instance is being set over here on awake. This is a Unity specific function that is called whenever this script is initialized. So on awake, we are instantiating the instance onto this. Since this little demo is meant to be a single player game, it makes perfect sense that the player is a singleton, since there is only ever meant to be just one player. Next, we can also see usage of a bunch of constants. Again, constants are values that are never meant to be changed. So in this little demo, it makes perfect sense to use a constant for the base movement speed, for the damage amount, and for the super timer max. Then we can see a whole bunch of events. We're going to see these in detail in a little bit. Then we've got a bunch of fields. And by the way, the serialized field here, this syntax is actually an attribute. This is something that I cover in detail in a lecture in the advanced section. Over here, this specific attribute, this is another Unity specific thing. It is just so I can expose these fields over here on the Unity inspector without having to make these fields public. If I were to just make them private without this attribute, then it would not show up in the editor. So in order to do that and keep the code clean, keep the fields private, in order to do that, they need to mark that serialized field private. Okay, then we have a bunch more fields. Then we got some inventory logic. We're going to see this in a little bit. Then we've got the update. This is another Unity specific function. Basically, the code in here is going to run whenever the frame updates. So if the game is running at 60 frames per second, these functions are going to run 60 times per second. We've got a function here to handle the object rotation. So that's the logic for how over here the pistol is rotating to face wherever I'm aiming with the mouse. Then there's some code to handle the items. I'm going to cover the inventory in a little bit. Then some code to shoot. Then we've got some standard movement code. So just some basic ifs, calculating a certain move vector. And then just moving the transform alongside this move direction. The transform is basically the game object in Unity. Then we've got the super, and let's begin by inspecting in detail over here the collisions. Again, this is another Unity specific function. This one has to do with the Unity physics system. Basically over here for all the objects that can be picked up, like for example over here the money object over here has a little collider. So this little box is a physics collider, and basically as the player goes inside of this collider, it is going to trigger that function. And over here this function will be called with whatever object it collided with. So the first thing we do is try to get a component. Again, this is another Unity specific function. This one tries to get any component of a certain type that is attached to the same game object. So basically, as the player collides with this money object, it is going to try to get some of these components. And specifically, it is looking for a component that implements the interface iGrabObject. So here we see an example of an interface. In this case, this is an interface that represents any kind of object that can be grabbed. So in this game, that's a money, that's a weapons, that's a potion, and so on. And the interface defines a bunch of functions which all objects that implement this interface must implement. So one of those is, of course, the money class. So this one, as you can see, it extends the monoBehavior class. This is the base Unity class, so this can be used as a component, and then it implements the iGrabObject interface. Then for the logic over here, it's pretty simple. This is really just some movement logic. So over here with the weapon, if I shoot a zombie, yep, there you go, the money gets spawned and moves a little bit, just to have a nice little bit of visual polish.